Hi, can you hear me?
Hi, Abhimanyu. Yes, we can hear you.
Okay.
Can you try to say something again?
Yeah, sorry.
Okay. I'm trying to see if it'll come out of the room speakers. Try one more time.
Hi.
Not quite. I have any idea how we got it onto the screen yesterday, what the input selection was? Solutions. So, Abhimanyu, can you check that we can hear you now and you should be coming through the room speakers now?
Yeah, I can hear you. Can you hear me?
Perfect.
Okay. All right.
Yep, you all sound good. So we're going to start off this morning with sort of a research presentation introduction from Sophie, and then we'll get going with your lecture, Abhimanyu. So
Okay.
it'll be
Yeah.
maybe about 10 to 15 minutes, and then we'll get started with you. But first of all, Sophie, if you'd like to come in. Did you send along the... it might be easiest if you bring up your laptop and just connect the Zoom and share screen. That's should be just one of the bookmarks in this. Yeah. Okay, everyone. Welcome to day two. They start to trickle in. Very closer to 9:30. First of all, Sophie has Randy volunteered to just pick up the end, which is what the fluid, right?
Yeah. Thank you. Hi, everyone. I'm Sophie. I'm an undergrad at UC Berkeley, and I'm working with Dr. Luke Kelly. I haven't given very many of these types of talks, so go easy on me. So with the discovery or detection of the gravitational wave background last summer and being kind of on the verge of detecting a single source supermassive black hole binary for the first time, Luke and I are focused on trying to search for multi-messenger supermassive black hole binary candidates. And we're in particular looking at the intersection between X-ray astronomy and gravitational wave astronomy to do this. So really quickly, when we talk about multi-messenger astronomy, we mean we're looking for electromagnetic signatures of a source as well as the gravitational wave signatures. Black holes themselves don't emit light, right? They're black, but we can look at the accretion disk around these systems because those are really hot and that emits radiation. So the main goal of this project is to determine if supermassive black hole binaries could be detected with the kinematic offset of this particular X-ray line called the iron K alpha X-ray line. And if so, what types of systems might we observe? And would we be able to see these emission lines at the same time as a gravitational wave signal? And if that's the case, what types of most likely parameters would these candidates possess? So Luke did a study on this, a similar study a while ago using an optical broadline, a hydrogen line that's emitted much farther out in the accretion disk. The results from his study were that it's not that promising of a tool to try and detect binaries because in order to have these two lines be visible, the emitting region of one needs to not be getting sucked into the gravitational influence of the other black hole. But you also need to have a close enough separation that you can detect these two separate lines offset from each other. So that's our motivation for choosing this X-ray line. It emits at a lot higher energy, so it's easier to see through the dusty torus that surrounds these types of systems. And because it's emitted in the inner accretion disk, you have a less likelihood of the emitting region being truncated by its companion. So the main theory that's important here is we have a maximum separation and a minimum separation of our system. So the minimum separation, at what separation do you get any closer than that? Does the emitting region of one black hole get disrupted by the other? And then a maximum separation, if they get any farther apart than this certain distance, then we won't really be able to see both spectral lines offset from each other. So you can translate those distances using Kepler's law and assuming circular orbits, because that's convenient, into a gravitational wave frequency regime. And this preliminary plot from, I think, last summer was pretty exciting because when Luke and I were looking at it, we were like, oh, this region of possibly detectable parameter space really well overlaps with the pulsar timing array frequency range and some of the LISA frequency range. So this was a little bit of an encouraging sign. We should keep looking. So the main way that we're approaching this project is to generate a lot of realizations of our universe or populations of black hole binaries using holodeck, which essentially allows you to plug in some initial parameters about your universe, such as how often your galaxies merge, what the mass of your black holes tend to be, and it spits out a population of black holes that then you can run your data on. So when you do that, for an example, it spits out something called a semi-analytic model, or a SAM, and it has 4 parameters: the total mass, the mass ratio, or in this case, the reduced mass, the redshift of your systems, and the observed gravitational wave frequency, or the observed orbital frequency. And it also tells you the number of binaries that possess those parameters. So then you can get a cool, pretty plot like this that kind of illustrates your parameter space. So, if you have around this binary mass and this observed gravitational wave frequency, you have this number of binaries that possess those features. So some preliminary results. In order to kind of splice the data, you start with your semi-analytic model, and then you start making cuts based on the criteria for the separation of these binaries. And then you get into needing a flux, an X-ray flux, that is bright enough for us to actually detect. So here, the background orange is the total distribution of binaries. The blue is all of the systems which theoretically should possess these dual iron lines. And the green is the systems which have a hard X-ray flux that's above a certain threshold. And that threshold is determined by the sensitivity of our instruments. So the data processing is also pretty dependent on the way we translate our luminosities from bolometric luminosity to X-ray luminosity. And that's where Dr. Renault's 2012 bolometric correction comes in. And if you use different bolometric corrections, like this one is from Shen et al. 2020, that changes the type of parameter space that your detectable region covers. So the next step is to generate lots and lots of semi-analytic models. The goal is to make like hundreds or 1,000 and run it all through our data pipeline, because holodeck does possess some inherent uncertainties when it comes to creating these models. So on the right-hand side here, all these plots are kind of small, but essentially I randomly selected of the 6 initialization parameters and generated a semi-analytic model. So there's 10 here, and then run that through the data pipeline to get out my detectable region of parameter space. And on the left here is the median over all 10 of those. So in theory, if we can make a ton and kind of average over all of those different parameters, hopefully it'll mitigate some of the uncertainties that are intrinsic to holodeck. And so far, it's looking pretty promising. We're getting like 0.0001% of binaries are detectable, but that kind of translates to like not a terrible number. Like this is 12,000 here with the Renault correction and almost 20,000 with the other bolometric correction. So looking okay so far. The next plot is, Luke hasn't even seen this yet. I made this last night at like 11. So the next step is making another data cut from the hard X-ray regime to just the flux from this particular fluorescent line. And when you do that, you actually get very few binaries. This was like 18 out of like a billion. But that's okay. So I'll talk to Luke about it and we'll see if it's good or not. And then these are all minimum fluxes corresponding to instrument sensitivity. The minimum flux required for Chandra to pick something up is around 10 to the minus 15 ergs per centimeter squared per second. 10 to the minus 16 is kind of the next generation of X-ray observatories, and 10 to the minus 14 is probably the most realistic one here. But these guys, there was nothing visible. So I think that was less than 10 minutes. So yeah, those are all my slides.
These is that parameters, or is that
So it's kind of both. Like the choice of parameter makes a big difference. So for example, if I double the rate of galaxy mergers, then I get way more black holes. And so I'm just going to end up getting way more detectable black holes in my universe. Just like if I adjust the average mass of my black holes, the process that computes that, and I get more massive black holes, I'll get more in my detectable region. Luke would be better able to answer the more technical aspects of holodeck's shortcomings, but within holodeck, the way that it calculates or evolves these systems to give you a final population, like it makes some assumptions in there and stuff like that. You mean, wait, let me make sure I understand your question. Regular X-ray emission versus reverse X-ray emission?
No, I mean, there's X-ray.
Oh, yeah. Yeah. Yeah, so the reason for kind of trying to look at all of these different minimum fluxes is to kind of look at, the past instruments, the present instruments, and the future instruments. So yeah, the next step also is looking at kind of breaking down the study based on what could we possibly see in the future, what would the sensitivity of a future instrument need to be to detect these things, would we be able to detect any with what we have now? So like the sensitivity of Athena and the XMM Newton and stuff like that is, we're looking at that. I can't really tell. Is there a question on Zoom or just people? Oh, okay. Okay, cool. Thank you.
Okay, so the first lecture of today is on pulsars and pulsar timing. This is where we start to get a bit more specific to our particular domain. I'm sure Abhimanyu will have a tutorial. And so for using that, you may want to go to the GitHub repository. Abhimanyu, will people need to download a notebook, or how else are you going to structure the tutorial?
So it's a total, I think 90 minutes, I guess. So I'm for the first 45 minutes or so, I'm going to give up like a normal lecture, and then after that I will show how to use Pint using a Jupyter notebook. So both of these things are in the GitHub repo. So please download them. There is a PDF, and then there is a IPython notebook. So.
Excellent. So if people haven't done it already, I put kind of a paragraph in the summer school Slack yesterday evening, and it's about getting the repository. So if you haven't cloned the repository yet, Kyle. They're not on the, okay, so we need to merge them?
It's already merged, I think.
Okay, never mind, Abhimanyu. I think your materials are there. So if people haven't cloned the repository already, then you're going to go ahead and do that. You'll need a GitHub account to do that. So while Abhimanyu is given 45 minutes of lecture, pay good attention to the lecture, but it's also an opportunity to quickly try to get an account if you don't have one, clone the repository, or if you really want to be impressive, fork the repository to make your own copy of it, and then clone that. So forking is good practice because it gives you your own copy you can mess around with without affecting the main upstream repository. And we'll put some instructions in the Slack as well, but essentially if you fork and then set the main upstream repository as such in your own copy, then you can pull changes down from the main upstream repository, incorporate them into your personal fork, and everything will nicely stay in sync. It's how people develop code to avoid tainting the main upstream repository. So we'll put some commands in there that you can try when Abhimanyu switches over to the tutorial portion. But first of all, I'd like to introduce Abhimanyu Susabanan, who's a postdoc at the Max Planck Institute for Gravitational Physics in Hanover in Germany, working with people such as Rutger van Hasteren and Bruce Allen and others. Abhimanyu is I would say now the chief developer of Pint, which is a recursive acronym. Pint is not Tempo 2, where Tempo 2 and Pint are all timing software for pulsars. So thank you so much, Abhimanyu, and please take it away.
Thank you, Steve, for the kind introduction. So, as Steve said, this is going to be an introduction to pulsar timing. This is going to be a slightly more basic introduction with sort of an info dump style. So, the idea is for you to, if you are a new student, to be familiar with the terms that we use in pulsar timing, and then you can go back home and Google them or use ChatGPT or something to get more information. So yeah, without further ado, let me start. Okay, so let me start with what are pulsars. So pulsars are pulsating sources with very stable pulse periods. This was discovered in 1963 by this lady named Jocelyn Bell Burnell. And on the left, you can see the discovery plot. You can see like tiny pulses there. These are single pulses that from a pulsar, and you can see that they are very evenly spaced in time. So these are very periodic sources. So we now know that these objects are rotating neutron stars, and these things were actually predicted theoretically by Zwicky and Bade in 1933, shortly after the discovery of the neutron. So they basically predicted that there could be a star that is made of neutrons. So so a little bit more about neutron stars. So they are formed from supernova events. So there can be like two types of such events. So one is a death of a massive star. If you have a star something like 10 to 25 solar mass or something, and it collapses after exhausting its hydrogen fuel, it would go supernova, and at the center of the supernova remnant, you would have a neutron star. Or if two white dwarfs collide or merge, then also you could have a supernova. Or if a white dwarf slowly starts accreting matter from a companion star and then goes above the Chandrasekhar limit, then it will also go supernova. And this type of supernova is called type 1a supernova, and that also can produce neutron stars. So the mass of neutron stars is of the order of 1.4 solar mass, if that is like basically the Chandrasekhar limit. And it could be up to three solar mass or thereabouts according to the model you are using. The radius of a neutron star is of the order of 10 kilometers, which is 6 miles if you are American. So these are mostly made of neutrons, and these are supported by neutron degeneracy pressure. So neutron degeneracy pressure is much stronger than, say, gas pressure or radiation pressure or things like that. And we know that the neutron stars probably, or most likely, has a solid crust and superfluid neutrons and superconducting protons inside it, but the exact structure and details of the neutron star interior is unknown. Neutron star, so the pulsars or neutron stars, they rotate very fast, and this rotation comes about because the star that gave birth to them, it was rotating. And when you collapse a star down to 10 kilometers, then according to angular momentum conservation, your rotational frequency has to go way up. So that's how they get some such rapid rotation. And they are also characterized by very large magnetic fields. So this also comes about due to the collapse, because when the matter is collapsing, the magnetic flux lines associated with the star, they cannot dissipate or escape. So they would collapse along with the matter, and when you squeeze the magnetic flux lines, you get a very large magnetic field, because magnetic field is flux divided by area. So these magnetic fields are of the order of 10 to the 8 to 10 to the 14 Tesla, which is very large. Despite the name, pulsars don't actually pulse. We see pulses because the radiation from the pulsar is coming from the magnetic poles, and the magnetic axis is usually misaligned from the rotational axis. So so whenever the beam of radiation comes in our line of sight, we see a pulse. So that is how we perceive them as pulsed sources, but they are actually emitting continuously. So on the right, you can actually see an optical image of the crab pulsar taken using a normal civilian camera. So yeah, you can see it blinking here if you look carefully. All right. So where does this energy come from? For pulsars, there are three types of mechanisms. One is called rotation powered pulsars, where the rotational kinetic energy of the pulsar, which is huge because it's like rotating so fast, is spins down, and that kinetic energy gets emitted as radiation. The second type is accretion powered pulsars, where the energy is coming due to the accretion from a companion star. So these kind of sources are usually spinning up rather than spinning down. And then there are magnetars, where the energy comes from decay of the magnetic field. So here is a plot of the pulsar population that we know of. I made it last week from the pulsar catalog, so it's probably pretty accurate. So we know around 3,600 or pulsars have been discovered so far, and as we have better and better telescopes, more and more are getting discovered every year. So here on the green circle we have these normal pulsars. They are called normal because they are sort of middle of the pack. They have like slow rotational frequencies and sort of average kind of magnetic fields. There are young pulsars, which are pulsars that have just formed, that formed very recently. So they are like spinning like a little bit faster than the normal pulsars because they are yet to spin down to that period. And there are
your audio was kind of cutting out occasionally.
Oh, okay. So yeah, my internet probably has a problem. Can you hear me now?
Yeah, we'll see how it goes. It might be on your side, but let's just see.
Yeah, sure. Yeah, so there are magnetars, which are highly magnetized pulsars. So we have detected a few of those. And then finally, there are millisecond pulsars. So these millisecond pulsars are pulsars with a few millisecond kind of rotational period. They are slightly different from other pulsars in the sense that they were not millisecond pulsars when they were born. Rather, they were normal pulsars that were spun up by accretion from a binary companion. So this is called a recycling. So it happens like this. So you have a star, and with a pulsar you basically have a binary star system. One of the stars is larger than the other, so that one grows old and goes supernova first and produces a neutron star. And then the second one also grows old and swells up as a giant. And then the first neutron star starts accreting matter from its companion. And so this accretion sort of transfers angular momentum to the neutron star and spins it up. You can spin it up to millisecond level periods, and then finally the companion also goes supernova, and it becomes a neutron star or a black hole or something like that. So in the end, we usually have a system where we have a pulsar with some kind of a compact object companion, and indeed most of the millisecond pulsars are found in binary systems. And what makes them special in the context of gravitational wave detection is that they are more rotationally stable than slow pulsars, which makes them excellent clocks. So a little bit more about the emission mechanism, how the pulsars are producing this radiation. So as I said, a neutron star is a huge magnet. You can consider them as a highly magnetized magnetic dipole. So, and this dipole is rotating at an axis. So when a magnetic dipole rotates, in its vicinity, you would have a huge derivative of the magnetic field, basically dB by dt. And that, according to the Maxwell equation, would create a very large electric field. And this electric field is so large that it rips electrons and charged particles out of the surface of the neutron star. So now what happens to these charges is that they can only move in basically one direction, because they cannot, there is a huge magnetic field and electrons cannot move perpendicular to the magnetic field, because if they do that, there will be a huge Lorentz force acting on the, which is V cross B. So they would basically orbit around the magnetic field line, and in doing so they would emit their energy as cyclotron or synchrotron radiation, and they would basically fall down to the magnetic field line with only their velocity along the field line remaining. So basically what they do is that they travel along the field lines like beads on a string. So now we have all of these electrons which are tied to the electron to the magnetic field lines, and the magnetic field itself is rotating because the pulsar is rotating. But at some point, because the pulsar is rotating so fast, the speed of rotation becomes equal to the speed of light, and these electrons and the magnetic field lines cannot co-rotate any further, because it would violate the special relativity. So this radius, or rather this area, this volume, is called the light cylinder. So the magnetic field lines that cross the light cylinder cannot come back and close. So they are open magnetic field lines. So so then what happens, since there's a huge magnetic field and there are charged particles, the electrons inside the light cylinder will sort of rearrange themselves to cancel out this this large electric field. But the electrons that are tied to these open field lines cannot do so, because they are not coming back, they are not closing. So they get accelerated along these field lines, and they get accelerated to such relativistic velocities that they start emitting gamma rays, which have enough energy to interact with the magnetic field lines and start producing electron-positron pairs. So these pairs again get accelerated, and they produce new gamma rays, and then the new gamma rays produce new electron-positron pairs, and so on and so forth, and you get a particle shower essentially. And this particle shower, at every stage of this process, you are losing energy. So at some point, you would get electrons that are relativistic, but not that relativistic. The energy they emit would be in radio. So basically, and that, as the theory goes, is how we get radio emission from pulsars. Okay, now let's come to how we observe pulsars and what the pulsar observations look like. Most of the pulsars are seen in radio and gamma rays. Some are seen in X-rays, especially accretion-powered pulsars. They are seen in X-rays. Some, very few, like the Crab pulsar, are seen in other frequencies like infrared, visible, or ultraviolet. They are very rare. Only very few pulsars are seen there. The radio, we are mostly interested in radio observations, so I will talk about that more. We do radio observations from very low frequencies like 100 megahertz to very high frequencies, several gigahertz. So if you look at a pulsar spectrum in radio, it's a so-called steep spectrum source. So if you look at this, this is a plot of flux density versus frequency, and you can see that it is much brighter at lower frequencies. So and less bright at higher frequencies, and this roughly follows a power law for many pulsars. So these such things are called steep spectrum sources. But the unfortunate thing is that the lower frequencies are affected more by the interstellar medium. I will talk more about that later. So even though they are brighter at lower frequencies, we can't really, some of them, it is harder to sort of observe them and study them at lower frequencies due to the interstellar medium. But it also has an advantage that at lower frequencies, you can actually study interstellar medium using pulsars. So it's pros and cons. Usually, in the initial plot, by the discovery plot, I showed you individual pulses of the pulsar, but those kind of pulsars are very rare. Most pulsars are much fainter than that, and so we cannot really pick out individual pulses or single pulses over the noise. So we can still observe, study them, but you cannot really see individual pulses. So the way we study pulsars without seeing individual pulses is through a technique called folding. What we do is that we take the whole pulsar observation, and then we sort of like co-add them, add the stack pulses on top of each other. So if we know the pulsar frequency beforehand, we know which chunks contain the pulses, and so we can like cut our observation in those chunks and then stack them on top of each other, and then if you add them together, the pulse would come out. So this is because if you add capital N number of pulses, the noise, since it is a random process, it only grows bigger as n to a square root of n. But the signal is a sort of deterministic process. So if you add a lot of these pulses together, the signal part would get stronger by a factor of n. So if you add n pulses, the signal to noise ratio would go up as a square root of n. So that's how we can study pulsars even without seeing single pulses. So the thing that you get after folding is called an integrated pulse profile. For the individual pulses, the pulses may remain stable for some pulsars, or it can vary a lot for some pulsars. But it turns out that if you fold a lot of pulses together, then the thing you get, the integrated pulse profile, is very stable. At least it is very stable for most pulsars most of the time. So here is what an integrated pulse profile looks like. So here you have the observing frequency, and here you have the pulsar spin phase. So what we have like folded all of the time information together, and instead we have remaining is this phase information. You see this kind of like a sweeping behavior, and that is coming because of the interstellar medium. I will tell more about that later, but you can correct this. This is called dispersion sweep, and you can correct it by applying a dispersion measure, and that is seen on the right hand side. And as you can see here on the left, if you have uncorrected dispersion, your pulse actually gets smeared because the different frequency pulses are arriving at your telescope at different times. If you don't correct for that, you would get just this kind of a smeared mess. But if you correct for that, you would get a very sharp pulse like on the right. So it is very important to correct for dispersion. I will tell more about that later also. So it turns out that the pulse shape of different pulsars is different. So here I'm showing a few pulsars, and for each of them, the pulse shape is very unique and it is stable. So you can treat the integrated pulse profile shape as a pulsar's fingerprint, at least most of the time. There are cases where this doesn't work, but for most of the vast majority of the pulsars and most of the time, you can do this. Okay, now let me sort of mention some phenomenology you would see in pulsars when you are doing pulsar observations. These things get discussed from time to time when you are doing PTA science. So there is subpulse drifting, where your pulse is made of multiple subpulses, and the subpulse like drift in phase over time. And there is pulse nulling, where the pulsar for some reason just decides to stop emitting light. So you would see a blank here. This is called pulse nulling. Then there is mode changing, where the pulse shape of a pulsar, the integrated pulse profile shape changes like abruptly between different modes. There is frequency dependent profile evolution, where the pulse shape is a function of frequency. So at least this we sort of understand why it is happening, because the different frequency radio waves are emitted from different parts of this cone of the pulse emitting region. So it is expected that you would have some differences in the pulse shape. And then there is pulse jitter, which is a stochastic variations in the shape of the pulse. So, and then there are giant pulses, which are like some pulsars, usually their pulses are pretty weak, but once in a while it would emit a pulse that is like orders of magnitude brighter than a normal pulse. So this is called a giant pulse. So I'm not going to explain any of these things in great detail, but these are things of interest if you decide to do, if you are doing pulsar science. So, okay, let me come to pulsar timing. Okay, so pulsar timing is the technique of tracking a pulsar's rotation using the times of arrival of its pulses. So that's a mouthful. What it means is basically that we see very periodic or very regular pulses, and so basically what we can like measure the time when the pulse arrived at a telescope, and we can use that to we can like utilize that to use the pulsar as a clock. That's what it means. So the way we measure the time of arrival, or TOAs, is by comparing the measured measured integrated pulse profile. If you look here, this scatter plot is the measured profile, and we can compare them against a model, which is called a template. So on the top you have a template, and in the second plot you see that it has been matched. So how much you have to move your template to match with your observed profile tells us when exactly the profile arrived at the telescope. And this process, even though it is shown in time domain, it is usually done in frequency domain, and because that turns out to be more precise, and that's how we get time of arrivals. And that also allows us to measure the uncertainty in TOAs and so on. There are two sort of paradigms for measuring TOAs. First is the narrowband timing, where we split our observation into multiple subbands. Subband is just a subset of a band, of a frequency band. So if you have like 100 megahertz of bandwidth, you may decide to split that into say 8 or 16 subbands or something like that. And for each frequency, we can measure one TOA. So what the advantage of this is that by doing this, we can actually measure what the dispersion is. So that's why we do. And also because as I mentioned earlier, the profile shape is a function of frequency. So if you like merge everything together, you may not get the best result. So by splitting them in frequency, you get like better accuracy in measuring your TOAs. The second thing is called wideband timing, where you treat the entire observation, frequency resolved observation, as a single entity, and then you sort of compare it against a two-dimensional template, which has a phase dimension and a frequency dimension. And this thing is called wideband timing. So this is a sort of new and upcoming field that is under people are working on very hard to make wideband timing work. But whereas the narrowband timing has been around for decades. So yeah. So once you measure TOAs from your observations, you get a bunch of TOA measurements, and these things are basically stored as TOA files. These are sort of text files called TIM files. So these look like this. So this is called the so-called tempo to this. Okay, actually, this is called the sort of IPTA format. It has, in addition to the actual TOA measurement, a bunch of other metadata as well, which is useful when you are doing the analysis. And you can sort of read a TOA file like this. At the top, you would have this format string. Format 1 is for tempo2 format, which is sort of the standard format we use for IPT observations. So the first string here is the name of the profile file. So this is mostly for information, just to understand which profile, which file this observation was, this TOA measurement came from. The second is the observing frequency. So if you are splitting your total observation into multiple subbands, then this observing frequency would be something like the middle of the central frequency of the subband. The third thing is the actual TOA measurement. And this is a very long floating point number. And it turns out that you cannot like store this in a normal floating point number. You need more precision than that. So these are stored in like extended precision floats, or if you are familiar with C or C++, long doubles. So this is an MJD. The TOA measurement is in MJDs, modified Julian date. The next thing, the thing in green, is the uncertainty in this TOA measurement. So this has units of microseconds. And the next thing, the thing in purple, is the code for the telescope. AO stands for Arecibo. And the rest of this stuff is basically metadata. These things as more information about what kind of observing setup was used, what kind of backend was used, what front end was used, what receiver was used, those kinds of things, and how long was the observation. So these flags basically tell us a whole lot about the observing setup, and this is valuable when you are doing the observation, because the TOAs taken using different instruments or different telescopes can have different properties, and so we need to be able to characterize them. So that's why there are like so much information, extra information here. Okay, so as I mentioned earlier, we can use pulsars as clocks by timing them. These are not, right now, they are not quite as good as our best atomic clocks, but they are still pretty good. And to do this, we must model all of the processes affecting the TOAs. So the TOAs are not just, so the pulsar is emitting the TOAs at regular intervals, but that is not the only thing that is affecting the measured TOAs. There are a bunch of extra things that contribute to your measured TOAs. Some of these things are deterministic, and some are stochastic. Some of these things are astrophysical, and some are instrumental. And this entire setup of all of these processes taken together, you can model them mathematically, and that is called a timing, and sometimes timing and noise model. So, so here is a sort of incomplete list of all of the things that can affect measured TOAs. I will not go into all of these things. You can, the usual suspects are pulsar rotation, obviously, and their rotation is not always stable. You can have rotational irregularities. You can have pulsar moving in a binary. You could have interstellar medium effects. You could have gravitational waves. You could have solar system dynamics and solar wind, and so forth, so on and so forth. You could also have like observatory effects, like the corrections to the observatory clock, or the radiometer noise, which is the noise, instrumental noise from the observatory, and things like that. So there is a huge number of these things we have to account for to sort of treat a pulsar as a clock, but we are able to do all or most of them. So here is here is a sort of mathematical formalism of what this looks like. TEM is the time of emission, or what we time of is the time of emission, the time at which the pulsar emitted the pulse. And TARR is the time of arrival, when we measured the pulse at our telescope. So this TRR and TAM are obviously not the same. This TARR are affected by delta clock, which are the clock corrections due to the inaccuracies in the observatory clock. Delta SS are the solar system corrections. Delta DM is the dispersion measure correction, which is due to the dispersion of the radio waves in the interstellar medium. Delta B is the binary correction. Delta GW is the gravitational waves, and so on and so forth. So once we compute this TEM, we can use that to compute the rotational phase of the pulsar. So this phi 0 is some phase offset, because we don't know how many rotations it has already had, because we don't know when exactly it was formed. So phi 0 has a huge unknown additive number, which we don't care about. This F0 is the pulsar frequency, and F1 is the derivative of F0. So as I mentioned, in most rotation-powered pulsars, it is emitting its rotational kinetic energy as radiation. So the frequency will not be a constant; it would be spinning down, and that is represented by this F1. And sometimes you would have higher derivatives of F as well. The timing residual is sort of like the observed TOA minus the TOA that is predicted by the model, and that you can compute by doing this calculation. Phi is the phase, phi minus the closest integer, this n phi is the closest multiple of 2 pi to phi. So basically what we are saying is that if our model is perfectly correct, then this whole calculation should give us a multiple of 2 pi, because each pulse, if we assume that each pulse is emitted at 0, 2 pi, 3 pi, 4 pi, and so on and so forth, we can this phi should be an integer. But say due to inaccuracies in our model and noise and so on, that is not the case usually. And so what we do is that we subtract out the sort of integer part from the phi, and then divide by the rotational frequency. And so this gives us a quantity that has dimensions of time, and that is called the timing residual. So the timing residual is the thing that you actually look at when you do pulsar timing. And here is an example of that. So different colors represent different sort of observing systems. And if your model is correct, then there should the what remains here, the timing residual, should be flat, and it should be consistent with 0, and there should not be any weird squiggles or outliers or anything like that. So this is what a sort of good timing model looks like. Okay, so the timing model is represented by a text file called a PAR file. PAR stands for parameter. So it basically lists all the pulsar timing model parameters and their values. So on the first column, you have parameter names. The PSR is the pulsar name, FEM is the solar system ephemeris we are using, and so on and so forth. The second column has parameter values, basically the values of each of these parameters. And the third column, which is optional, has can have like ones or zeros or nothing. So if you have 1, then it is telling the timing program to consider that parameter as a free parameter and fit for it. And then finally, at the fourth column, you have measured uncertainties. So basically, when you are fitting a model to your data, You always get your measurements with some uncertainties, and those uncertainties for the fitted parameters are listed here. So if you look, so the uncertainties are only there for the fitted parameters. So these are the sort of two files you would have when you say pulsar data. You would have a par and a TIM file. So always the pulsar data is distributed in this way. You would have a par file and a corresponding TIM file. A par file is the model and the TIM file is the data. So yeah. And we have to be able to fit a timing model to TOS, but because we don't know what the correct timing model is a priori, and that is done by different types of least squares fitting. So when there is no correlated noise, I will come to what correlated noise is later. When there is no correlated noise, we can do weighted least squares fitting. This is your usual chi-square fitting. Basically, you divide your timing residuals Ri by sigma I, which are TOA uncertainties that we saw in the TIM file, but scaled by some factors for various reasons. And then you square them and then you add them. And you can also represent them in a matrix way, R transpose N inverse R, where this N inverse contains 1 by sigma I square terms in the diagonal. If you have correlated noise in your model, then you will have to use the generalized least square fitting, which has a chi-square of this form. It can be written as R transpose C inverse R, where the C contains this N we saw before, that is the uncorrelated noise part, and then it also has this U transpose phi U part, which is a reduced rank approximation for the correlated noise. And I think other lectures would explain more about this, so I will not go into the details. And ultimately what you do is that you minimize this chi-square, which is sort of related to the likelihood of your data. And when you minimize this likelihood, that would give you a maximum likelihood estimate of your timing parameters. And that is what you would see that would populate in this kind of a par file along with the uncertainties. Okay. So now let's look at the timing model components one by one. So you have pulsar rotation, which is so the pulsar is spinning down because it's converting its rotational kinetic energy into electromagnetic radiation and possibly gravitational radiation. People are looking for it but haven't found. So we have this equation that we saw earlier, and it is important to understand what the timing residuals would look like if we have one of these things wrong. So for example, if we have a wrong F0, then your timing residual look like a straight line. It is not consistent with 0. It has a slope, and it has a slope. So this is what your timing residuals would look like if you have a wrong F0. The second plot is what you have if you have a wrong F1. It basically looks like a parabola. So so look out for these kinds of sort of signatures when you are doing timing, because by looking at the shape of these sort of parameters, you sort of get an idea of what parameter of your model is wrong. So oh, by the way, this phi 0 is a totally arbitrary sort of offset constant. So you can either fit for it or you can just subtract it out in some way. Basically doing a weighted average of your timing residuals. So this phi 0 does not really have any physical information in it, because because we don't know how many cycles it has been since the pulsar formed. This phi 0 has a very large sort of unknown, like 2 pi n kind of unknown additive constant in it, which we cannot measure. So whatever we can measure in 5.0 is totally dependent on your instrument and so on. So if this 5.0, the measured value at least, is not really a physical thing. It is just there to make sure that your timing residuals have an average of 0. Okay, so there are glitches which happens because sometimes a pulsar abruptly changes its rotational frequency. So if your pulsar does that, then you have to add this phi glitch term to your phi expression. These are rare in millisecond pulsars, which is fortunate for pulsar timing arrays. But and here is such a rare glitch in millisecond pulsars. But these things are more prevalent in normal pulsars and younger pulsars. So this is how a glitch would look like in your timing residuals. You would basically have like a sort of a ramp-like signal, basically, or like a triangle, or like an angular kind of shape, where two parts of your data have like two different frequencies. So, and this is what you look out for. You could have spin noise, also called achromatic red noise. So this is basically a slow stochastic wandering of the spin frequency. This is usually modeled as a Gaussian process with a power law spectrum. Again, this would probably be covered in other lectures, so I will not go into detail. And in your timing residual, this is what your red noise looks like. Regardless of the frequency, all of the TOAs basically go for a random walk, and this is what it will look like. This would usually be like stronger at lower frequencies, so that's why you see a sort of longer term signal, and that's why it's called red noise, because you have more slow frequency component than high frequency. So and this is one of the correlated noise components I mentioned earlier. Okay, so you can have pulsar binary motion. So if the pulsar has a binary companion, it affects the TOAs in three ways. One is Romer delay, which is sort of like the geometric delay, because the pulsar is moving around. Basically, when the pulsar is at different points in the orbit, the light travel time it takes to reach us would be different. So that's Romer delay. Shapiro delay is due to the fact that the binary companion is distorting space-time in its vicinity, and when the pulsar signal travels through that space-time, it gets a delay, which is time dependent because the companion is moving around. The Einstein delay is basically also a relativistic effect. It is a combination of two things. One is time dilation due to the motion. So the pulsar is moving. So due to special relativity, you would get a time dilation. And the pulsar is sitting in the gravitational field of the companion. And due to general relativity, that also causes a time dilation. And both of these things combine to give us the Einstein delay. So different types of binaries, we use different binary models. So the DD stands for Damour and Derival. So that is used for sort of relativistic binaries with significant eccentricity. So it also has a bunch of like relativistic corrections like Shapiro delay, Einstein delay, and so on and so forth. ELL1 stands for E eccentricity less than 1. This is used when you have a very small eccentricity, almost circular kind of orbit. When you have a very small eccentricity, you can do a different type of parameterization and etc. So that's why you have a different model. And depending on the geometry and the orientation of your binary system, you could have different models, because based on the geometry and orientation of the system, the actual parameters that we use to describe the binary will be different, because different parameters, maybe in some cases one parameterization would be better, but in some other cases that parameterization may not be that good. So that's why we have different binary models, and you'd see them as binary keyword in the timing model. So if we go back here, I think we have we have this binary DD here. So this is a DD binary, and then we have the binary parameters. So sorry, I lost it. Yeah. So here is what some of these wrong model looks like for binaries. So if you have a unmodeled binary Shapiro delay, you would see this kind of spiky feature when you plot the timing residuals as a function of orbital phase. And if your projected semi-major axis is wrong, you would see this kind of a sinusoid or a sort of period or sort of sinusoid kind of thing. For less eccentric binaries, this would be a more of a spiky thing if you have a more eccentricity. And for each of these parameters, you can like experiment and take a look at what these timing residuals would look like. Then now we have the interstellar dispersion, which I have mentioned earlier. Basically, what happens is that the free electrons in the ISM disperses radio waves, and the refractive index of the ionized ISM is electron density times the radio frequency to the -2, and this would appear in this plot. Your different frequency signals would arrive at your telescope at different times. And if you integrate this NE or along the line of sight, you would get a thing called dispersion measure. This is the quantity that like pulsar astronomers use to describe this effect. And if you have a wrong DM in your timing model, you would see this kind of sort of parabolic kind of shape when you plot your post-fit residuals in against observing frequency. So, like I said here, different effects have like different different plotting things where you can see this effect. So again, the interstellar dispersion is time dependent. I will not go into much detail. So this actually introduces a correlated noise in your pulsar timing. You also have interstellar scattering, which comes about because of the inhomogeneities in the ISM. So when you have inhomogeneities in your propagation medium, you will have multi-path propagation, and the same pulse at the same frequency would reach us at different times due to through different paths. And what that does to the pulse is basically that at lower frequencies it gets smeared out. And so this is called interstellar scattering. And gravitational waves can also affect pulsar timing, but I will not go into this because that's next lecture. You have solar system dynamics. Like the binary system, solar system also introduces Romer, Shapiro, and Einstein delays. And we know where the solar system objects are at any given time because the space agencies are tracking them, and they publish these solar system ephemerides periodically. So we can use that to calculate these solar system dynamics, and they also depend on the sky location of the pulsar. So, for example, this kind of sinusoidal variation with 1 year period is what happens when the sky location is wrong. And if you don't include solar system Shapiro delay, you again will have this type of a spiky feature in your residuals. So again, now we come to instrumental effects. Clock corrections are needed because the TOAs are measured against the observatory clock, and these clocks are stable in short term, but they are not very stable in long term. So we have to convert them to a international time standard. So that is done by measuring the difference between the observatory clock and some standard clock like the GPS clock, and then like noting down the differences. And and ultimately what we do is that we transform the observatory TOS to either the barycentric coordinate time TCB or the barycentric dynamic time TDB. So you also have the random noise coming from the observatory. This is called radiometer noise. This is an uncorrelated noise, and usually is assumed to be Gaussian, and this the TOA measurement uncertainty sigma I that I measured earlier gives a sort of good approximation for the radiometer noise. So this is a flowchart of how exactly we calculate the chi-squared from all of these effects by incorporating all of these effects. I will not go into this in detail. Okay, so now coming to more practical things. There are multiple pulsar timing packages we use. For the TOA generation is done using things like pulse archive, pulse portraiture, and so on. Pulse archive is for narrowband, and pulse portraiture is for wideband. If you want to do timing in a frequentist way, there are packages like Tempo 2, Libus Tempo, which is a Python wrapper for Tempo 2, and Pint, which is a pure Python package. Tempo is Fortran and Tempo 2 is C++. If you want to do timing in a Bayesian way, or if you want to do noise analysis, you can use things called like Tempo Nest, which is written based on Tempo 2, and Enterprise. These things Enterprise can actually also do gravitational wave analysis. And we also have like PTA specific or experiment specific timing pipelines. The nanographs pipeline is called Pint-Pal, which is used for all of nanographs timing analysis. Okay, so let me now come to the pulsar timing with Pint part. This is going to be a demo, but before that, let me just give you a brief introduction about Pint. So Pint is a pulsar package for Python package for pulsar timing. This was written using NumPy, SciPy, and AstroPy. So as much as possible, we have decided to use like existing packages, because those are well tested and written by smart people. So yeah, and Pint you can use in different ways. There's a GUI called Pint-K. There are command line scripts if you just want to do something quick and dirty. Usually, if you want to do proper analysis, it is done using Jupyter notebooks or the GUI. And if you want to do automated timing or do pipelines or something like that, you can also do that using Python scripts or pipeline kind of things. So this is a gist of what exactly Pint does. So it takes TOAs, an initial timing model, which may not be the best timing model, a solar system ephemeris, which comes from space agencies, and clock corrections, which comes from like some international agencies that track that sort of thing. And we apply Pint, and in the end, we get timing residuals that I showed earlier. So it should look flat and it should be consistent with 0. And we get an updated timing model. So this is sort of a very basic picture of what Pint does. Okay, now let us go to the Pint demo. So before that, while I change this, do we have any questions?
Manu, did you hear that?
No. Can you please repeat?
You might just check.
Hi, I was wondering why we consider the rank-reduced formalism to be an approximation or accounting for the noise in the covariance matrix.
Can you please repeat? I could not hear the full sentence.
Yeah, I was wondering why we consider the rank-reduced formalism to be an approximation when we're accounting for noise in the covariance matrix.
Okay. So in rank reduced formalism, what we do is that we treat the model the correlated noise as being sort of constrained in frequency. So we only consider the components of this model that is like from a certain low frequencies to a certain high frequency. So we don't consider components beyond that. So the problem comes when the noise components outside of this frequency range become important. So then your approximation would no longer be valid.
Thank you.
Yeah.
And can I ask my other question quickly? My other question was, I was wondering why we choose Gaussian processes for a lot of our noise models that we're using. Is there a reason why we choose to do that?
I'm probably not the best person to answer that. My understanding is that the Gaussian processes are the easiest to model because the Gaussian is the sort of default distribution. And so I guess that's the main reason why. And for example, if you consider the radiometer noise to be a Gaussian process, you can write your chi-square or the likelihood function in a very, very simple way. So that's probably part of the reason. And there may be more involved reasons as well, but I'm not the right person to answer those.
Thank you.
Part of it is also the set even if you have some really non-standard.
Okay. Okay, since we are sort of being close to time, let me start with the Pine demo.
Manu, I think we had one more question as well
okay.
from Levi and from online.
Okay. Can you please repeat that one? I could not hear.
Vidit has a question, and then we've got another question in the room.
Okay. Yeah. Hi, Abhimanyu. Yeah. Can you hear me?
Hi. Yes, I can hear you.
Yeah. So you said while fitting for the pulsar's parameters, if we fit them wrong, we get several kind of trends in the timing residuals. For example, we get a linear trend or a quadratic trend or some things like that, right?
Yes.
So what do you exactly mean by fitting the parameters wrong? Like, what does this wrong fitting mean?
No. I did not. Okay, sorry. I did not say fit the parameters wrong, but I said have the parameters wrong in your timing model. So for example, if you have a pulsar with 100, which is like emitting at exactly 100 hertz, but for some reason you some of your earlier measurements you got like 100.1 hertz as your frequency. So and when you if you use that model to time your newer better observations, since the actual frequency of the pulsar is 100, you would see a trend like this, like a linear kind of trend. So that's what I meant. So and then if you fit for that, you would get the correct answer, which is 100.
Okay. Yeah. Okay. Thanks.
Yeah.
Okay, we've got one more question in the room from Levi.
Hi, Abhimanyu. Thank you for the talk. You were talking about how generalized least squares is used for fitting the timing model when there's the correlated noise present. And you said there was the spin noise. That was a form of correlated noise, as well as the DM variations over time. What are there any others other than those two, or is that it?
Yeah. So there is there is pulse jitter. So what pulse jitter does is it introduces correlated variations in your correlated variations in your profile shape, and since that is a stochastic process, you would get a noise associated with that, and the sort of the uncool thing about it is that all the profiles, all the subbanded profiles in your one observation are sort of like changing together. So the noise that you get would be correlated across different frequency channels in your observation. So that is usually called the E-core in pulsar noise analysis of timing. And there is also scattering noise, which is like time-dependent interstellar scattering, which introduces a sort of like a frequency-dependent noise, which is not new to the -2. New to the -2 is dispersion, but it could be something like new to the minus. Sorry, excuse me, new to the -4 or something like that. There are also weirder, more esoteric things like band noise or group noise or things like that, which I don't understand. Yeah, there are a bunch of those things.
Thank you.
Okay, so we can transition into the demo now. Is there anything in particular that people should note while they're loading the notebook itself?
No, they need to have Pint installed, and Pint basically installs all the necessary things. So that's basically it. Yeah.
Okay, so when people open their notebooks or open the notebook within VS Code, they need to make sure that the environment that they created yesterday is operating for that particular notebook. And that should ensure that Pint is available for you to import.
All right, so let us start. Okay, so this was for IPTA student week, so I forgot to change that. Anyway, so
before you get started properly, Abhimanyu, I just want to make sure that no one in the room is left behind with the notebook. So has everyone been able to open the notebook to at least activate their environment and to say execute the first cell there that is doing Pint import commands? Any problems at all? Okay, wow. So then you can go ahead, Abhimanyu. Thanks.
Yeah, thank you, Steve. Okay, so the first thing we do is reading a parenting file, because that's our data and the model. So we for that we need to import Pint first. So Pint, so the function that is used for like importing data is called get model and TOS. It is in the pint.models module. And the second thing is pint.config.example file, which is a function that gives us access to the example data files that are distributed with Pint. So yeah, let me run that. That has been imported. And the second thing you might want to do, which I definitely like to do, is to set the log level to warning. Otherwise, Pint will just keep spewing error and like info messages at you and debug messages, which I find very annoying. So you might want to do setup log level equal to warning. But if you are a very cautious person, you might not want to do that, which is perfectly all right. It's up to your discretion. So these example files are stored in this directory. So this is in my system. So your system will have a different sort of folder name. So this is in like Pint data / examples. So all this example file command is doing is basically that it is foo.txt. If I do foo.txt, it would just like append this file name. It is all it is doing is giving me a file name. So there is nothing like strange going on under the hood. Sorry. All right. So the way we import a data is by doing model, TOS equal to get model and TOS. Then the first thing is the par file, which contains the model. And the second thing is the TIM file, which contains the TOS. So this may take some time. Okay, I forgot to do the setup log. Okay, so if I run that again, the error messages will disappear. So now I have now I have a model object and a TOS object. And this get model and TOS has a lot of like different options. You can take a look at them and like sort of try to search what each of those things mean. So this is a very flexible function, and it gives you like the freedom to do a lot of things while loading the file, the TOS and model. Two useful things you may want to take care if you work with people who work with Tempo 2 is that the Tempo 2 par files, Tempo 2 uses the TCB timescale by default, whereas Pint uses the TDB timescale. So to read some of the par files emitted by Tempo 2, you need to set this thing to true, allow TCB equal to 2. And similarly, there is a sort of timing model called T2 in Tempo 2, which is sort of like a catch-all timing model, which is not there in Pint. So to read a par file with T2 timing model, you need to do allow T2 equal to true. So this is just for like interoperability with Tempo 2. You can like look at this help and figure out what each of the things are. Okay, so now I want to take a look at what is inside this model. So if I do print model, I will get a par file representation of this. On the top are a bunch of comments which are indicated by hash. It basically tells me who created this file. I created it, what system it was created in, which is important because when you do data analysis, sometimes different systems behave differently and you get weird results. So, and what operating system was this in, because operating system can misbehave and you will get weird results sometimes, and what version of Python this was, and so on and so forth, and the date and the Pint version. This is also important because sometimes Pint may have bugs, and by looking at the version, you can figure out whether what bug is there or not there, and so on. Okay, so, and like I explained earlier, it has these like parameter names, the parameter values, fit or no fit, and the and the parameter uncertainties. So each of these parameters we can access like this. So if you do model dot some parameter name dot quantity, it will give a AstroPy quantity object. So this is an object which has a which has a magnitude and a unit. So this F1 is the derivative of the spin frequency. So that has units of hertz per second, or second to the -2. But there are also other other types of like parameter values which can have other types. So for example, the PSR, which is the pulsar name here. So that is a string. So you can't fit that because that's arbitrary. There's a P epoch, which is the epoch of the spin period variations. So that is a date. So that is stored as an AstroPy time object. Again, this planet Shapiro tells the Pint whether to apply the Shapiro delay corrections due to the planets like Jupiter or Saturn. And that is a Boolean. So that's a yes or no kind of type of thing. So that is, so for example, this dilate frequency, no, TM data, no. So these kind of things are like stored as Y or N in the par file. Okay, so you can get a list of all the parameters that are there in the timing model by doing print model.params. So that gives you a list of strings, which you can then use in whatever way. So if you want to only see which are the free parameters, the parameters that you can fit, that you can do model.free_params, that would give you a list of all the free parameters, basically the parameters which have like 1 associated with them here. This RA and DEC and F0 and F1 has 1s. So that is what free params is. There is also another interesting list, print model dot fittable parameter. So this fittable parameters are the parameters which you can actually fit, and free parameters are the parameters that you are fitting. So actually this PX, for example, and PMRA and PMDEC. So this parallax, PMRA and PMDEC are proper motion. So for example, the parallax and proper motion are not included in the free parameters. So you can also include them and fit for those parameters as well. So NESW is the solar system, solar wind electron density. DM and DM1 are the dispersion measure and the dispersion measure derivative, and so on and so on. So these two things are sort of important, and fittable params basically tells you which parameters you can fit even if you are not actually fitting for them. And the parameters like P epoch, start, finish, and so on, those are not included in fittable parameters, cannot be fit because Pine doesn't know how to fit them. Okay, now let's like take a more in-depth look at the model. So if you do model.components, it gives us a sort of string that contains all the component names. If you do model.component.keys, it gives me a list of all the component names. So there is an app space, which is sort of like which represents a TOA, reference TOA, with respect to which everything else is calculated. Spin down is spin down, as I mentioned. Astrometry equatorial is basically solar system roamer delay in equatorial coordinates. So you can see RA and DEC here, RAJ and DECJ. Troposphere delay is due to the troposphere of the Earth. Solar system Shapiro is solar system Shapiro delay. Solar wind dispersion is dispersion due to the solar wind. Dispersion DM is basically interstellar dispersion, and so on. So, and now let's take a look at the TOAs. The first thing you need to do while after getting a TOS is to like look at what exactly it contains. So you can do TOS.print summary. That would give you some like text summary of TOS. There are 62 TOS. There are 0 commands. Commands is like these things that you add to your TOA file to tell the timing program to like change the phase or add some extra time delay here or something like that. So there are no such things here. Number of observatories is 1. So it basically tells me that all of the TOAs are from GBT, the Green Bank Telescope. So it tells me the MJD span. It tells me that the date span, which is like same thing as MJD, but in a different format. It tells me the minimum and max frequencies. Tells me is the minimum and maximum uncertainties. The error is sort of a misnomer. It should be uncertainty, which is basically telling us what the TOA uncertainty is, and the median uncertainty. Okay, so the TOAs are internally stored as a AstroPy table. You can look at the column names. So if I look at the column names of this table, I have an index which is like 1, 2, 3, the just number of the TOA. MJD float, and those kinds of things are like different representations of the actual arrival time. The most important thing is TDB-LD, which is a long double representation of the TOA in the TDB timescale, which is this TDB-LD is the thing that is actually used for computations. And there are a bunch of other things. Obs is observatory, freak is frequency, observing frequency, error is uncertainty, and so on and so on. SSB, these things are solar system ephemeris vectors. So SSB obs pose, for example, is so the vector going from the solar system barycenter to the observatory. This is the vector, this is the velocity of the solar system barycenter with respect to the observatory. This is the position vector goes from the observatory to the sun, the center of the sun, and so on and so forth. So notice that there is a SSB and sun separately, because that is because the solar system barycenter is inside the sun, but it is not the same as the center of the sun. So that is why like there are two different things. So now let us look at the residuals here. So that is done by using this thing called a residuals object, which lives in pine.residuals. So you can create it as residuals TOS.model, and then TOS.getMJDs gives you the MJDs of the observation. Res.calc time residuals.calc time residuals that gives you the actual timing residuals. Res.get data error gives you the scaled TOA uncertainties. I earlier mentioned that the TOA uncertainties are an approximation of the radiometer noise. So sometimes it is underestimated or overestimated due to the idiosyncrasies of your TOA measurement algorithm, and sometimes you have to like scale them to be consistent with observation. So this get data error function actually gives you the TOA uncertainties after applying those corrections. So as we can see, the x-axis is MJD and the y-axis is TOA. It is centered at frequency. It is centered at 0, good, but it is not flat. It has this kind of sinusoidal kind of shape. And if I look at these numbers carefully, it is like this thing has a period of 1 year, which as we saw earlier is an error in the sky position. So we can also look at the chi-square, reduced chi-square. So the reduced chi-square should be close to 1, but it is not. So which basically again tells us that this is not a good fit. So now we want to fit and get the actual correct numbers. So that is done using the fitter class. So we can create a fitter object by calling fitter.auto, which looks at the model and the TOAs and decides which fitting algorithm best fit the situation. So if I do that, I get this thing called a downhill WLS fitter. WLS is weighted least square, and downhill is sort of like a robust algorithm for fitting. So this is the fitter object that I'm going to use. And fitting is very easy. You just call fit TOAs on this fitter class. Fitter object. And this max iter is the maximum number of iterations. So sometimes the fit does not converge after just one iteration. So you have to do multiple iterations. So it usually, if it does not converge even after like 10, 20 iterations, then there is something wrong with your model or something wrong with the fitting system. So that is something we may have to look at. So now that it has fit, I can like plot the post-fit residuals, which are the good residuals. Okay, so that again, a TOS.getMJDs gives me the MJDs. Fitter.residuals.calc time residual gives me the timing residuals, but this time I'm getting the residuals from the fitter object. So these are the post-fit residuals. Again, I'm getting the data errors from the fitter object. These are the post-fit errors because you can actually fit for these scaling factors called EFACs and EQuads for the error in Pint. So you should be, when you are plotting post-fit residuals, you should like always you take the error from the fitter object. So now it looks much more flat, and it is consistent with 0, which is good. We can also see if there is a DM error in it by plotting it against frequency. So that we do by like doing TOAs.getFreaks, which gives me the frequencies of the observation. And if I do that, it again looks flat, which is good. And there is no such like no clear, so that parabolic like shape that we saw when you have a wrong DM. So this is a good fit again. Yeah. So now if I do the post-fit chi-square, which comes from fitter.receipts.chi-square underscore reduced, it is close to 1. So this is a good fit. So now I can like plot the post-fit model. So I can print ftr.model, and it will give me the post-fit model, and we can actually compare the pre-fit and the post-fit model by doing doing model.compare. So what I'm doing is the model is the original model, and ftr.model is the new model, the post-fit model, and I can do model.compare, and that emits a bunch of warnings, and for some reason I can't see the output. Okay. Okay, let me skip that one. So please look at this. It basically gives you a parameter by parameter comparison of the two models. And if I want to save my my post-fit par file, I can do it by ftr.model.write_par file and whatever name you want. So I can do that, and that gives me, that basically writes this post-fit par file to disk. Okay, so now we can, okay, how long do I have? Okay, I have 5 minutes left. So you can like manipulate this TOAS object in different ways. If you just want one TOA, you can do that using the square bracket operator. So TOA 0 is the first TOA. If you want a range of TOAs, you can do the square bracket operator with this indexing notation. If you want a selection of TOAs, you can do again the square bracket operation with either a list of indices or a NumPy array which contains true and false values. So it would like extract all the TOAs which either has those indices that you have given, or which like have truths in the array that you have given. So that is also there. So this is useful, for example, for like throwing away outliers and so on. So and you can actually look at the observatory of the TOAs by calling this square bracket operator with obs, and you can also do different. You can also call like get flags by using this thing. And if you have like two TOAs objects, you can like sort of concatenate them by using the plus operator. There is also this adjust TOAs function, which can sort of like shift the TOA values. Don't do this if you don't know what you are doing, because it can destroy the data contained in your TOAs. But if you are doing simulations or something like that, then this adjust TOAs function is useful. You can you can get the pulse numbers of each TOA by you doing compute pulse numbers and then doing get pulse numbers. So this gives you the pulse number associated with each TOA. Here you can see that there are multiple same pulse has like multiple TOAs. That is because we have a narrowband observation. So that observation had like multiple subbands. So that's why there are multiple TOAs with the same pulse number. There are some other interesting derived quantities. So for example, there is solar elongation, which is called sun angle in pint. There is barycentric radio frequency, which is the radio frequency that has been corrected for the solar system Doppler effect. There is the total DM, which is the total dispersion measure that is coming from your model. If your model has like multiple dispersion measure multiple dispersion measure models, things like interstellar dispersion and solar wind dispersion, then total DM gives you the total dispersion measure. D phase by DTOA gives you the topocentric pulse frequency. That is the pulse frequency that you actually see from Earth. This is not the same as the emission frequency. The frequency at which the pulses are emitted, because that is modified by the solar system motion and the motion of the binary. So this D phase by DTOA basically gives you the topocentric frequency. So here, when I'm plotting it, I see that I have like this sort of annual variation in it, which is just the motion of the Earth in the solar system. You can also fit for white noise, which I am not going into because I'm out of time. Yeah, thank you. Please try it afterwards.
Thank you very much, Abhimanyu. That was fantastic. Was there anyone in the room or online that had questions about parts of the tutorial? Atarva, go ahead.
Hi. Yeah, thanks for the talk. I just wanted to know what's the main difference between a tempo 2 fit and pint fit. So pint does this iterative process. So how is it different from tempo 2?
So the basic theory or the basic principles are the same. There are like differences in how exactly the fitting algorithm is implemented, but those are like sort of implementation details. So ultimately the fit, the final product that you get from tempo 2 and pint should be like consistent with each other. So there are like no sort of major sort of mathematical differences in how these things are done. The algorithms are slightly different, but those are mostly implementation details.
Yeah, and I think you slightly touched upon that before, but sometimes the fit doesn't converge in pint, but if I run the same thing in tempo 2, it does converge. So
yeah,
like
so though that again goes back to the way like these algorithms are implemented. So basically what the problem is that if your starting point for the fit is very far away from the true value, then we are both tempo 2 and pint uses a linear fitting algorithm. So if the starting point is far away, then the linear fitting is not guaranteed to converge. So that is basically what happens. So there are cases where pint fails but tempo 2 succeeds, and vice versa as well. So these are like sort of the details of the implementation matter for the convergence of like different cases. So yeah.
So like in that case, is it possible that if I first do a fit in tempo 2, update my PAR file with that fit, and then use this updated one, so that then the pint will, get a better.
Yeah, in some cases that can give you the right answer, but if you are using tempo 2 to begin with, then there is no point. Like there is no point in doing it like twice, right? Also in pint there are like multiple fitting algorithms. So this downhill fitter is one of them. There is also the non-downhill fitters, which are sort of which are like more similar to the tempo 2 ones. So those algorithms sometimes do better in certain type of problems. So one thing you can do is like use a different fitter and see if it converges. Yeah.
Okay. Yeah. Thanks a lot.
Yeah.
Yeah. So Nikita has a question in the room. Did you want to come up to the hall maybe?
Hi, Abhimanyu. Sometimes while doing the reduced chi-fit, even on obtaining a chi-square value close to 1, the data is either overfit or still remains underfit, even on repeated attempts. So what's the best way to deal with that? Is it to remodel the data, or is there a better way?
I don't have a satisfying answer for you. That basically depends on your data. Sometimes your data may have like unmodeled effects. For example, if you have like very significant profile evolution, you may need to use like things like FT parameters or things like that, or you may have things like like pulse jitter, then you will have to use eCore. Or you may have like unmodeled effects like binary Shapiro delay, or a dispersion measure variations or scattering variations or things like that. So like without looking at the specifics of your pulsar, it is very difficult to tell what exactly is going wrong. So the best advice I can give you is like plot your the timing residuals against different like axes. For example, plot it against the sun angle, that will tell you if there is a solar wind or something like that. Or plot it against the frequency, that would give you a hint about like FT parameters, DM, and scattering variations and so on. And plot them against the day of the year, and that would tell you if there is a solar system thing going on. So those kinds of things are there. So it is very, very pulsar dependent. And sometimes you have to like use dirty models, like uh, like invent models on the fly to fit your data. So it happens.
Thank you.
Yeah.
All right, any other questions in the room? If not right now, then I'm sure you can contact Abhimanyu on Slack or on email. But let's thank Abhimanyu again for the lecture and the demo.
Yeah, thank you for having me.
Absolutely, yeah, it was fantastic. Thank you very much, Abhimanyu. All right, so we'll take a sort of 10 to 15-minute break now. There's some slightly warm coffee still at the back of the room and some snacks. And we'll come back with me talking about how pulsar timing is affected by gravitational waves. Okay. But, sorry. Oh, yes, I apologize for our secrets. All right, everyone, let's get started back. I'll try to talk all the way up until lunch arrives today, which should be 12:30. So we've seen yesterday how you reduce gravitational waves, how they come about in Einstein's general theory of relativity, and this morning how pulsars work, how pulsar timing works. And Abhimanyu mentioned that one of the mechanisms that can affect the timing of pulsars is the influence of gravitational waves. So whenever pulsar astronomers time the pulsars, they're not thinking about gravitational waves, they're thinking about more deterministic effects. Deterministic effects that are much, much larger than the gravitational wave influence. So for example, the period of the pulsar, the spin down rate of the pulsar, other things like the interstellar medium, these are all much, much more massive effects and influences on the timing of pulsars than gravitational waves are. Gravitational waves cause very, very small changes in the timing of pulsars. So if you've got a millisecond period pulsar, then gravitational waves cause a change to the arrival time of one of the pulsars, which is maximum 100 nanoseconds. Okay, so it's a very, very small effect on the timing of these pulsars. So here's my little graphic that actually comes from a Nanograph Space Public Outreach talk So here we've got a train of pulses propagating from the pulsar to the Earth. We can time these very well. We can build up very sophisticated and precise models of when the pulses should arrive. And in fact, these pulsars can be timed, and we can not lose track of any of the rotations for very, very long periods. So there are lots of things taken into account that Abhimanyu mentioned in his talk and that you now have some experience with. But we can also have an influence from gravitational waves. Gravitational waves will change the proper separation between the Earth and the pulsar. So this little ruler is going to show that we've got an expanding and contracting length between the Earth and the pulsar. So the photons will either take longer or less time to arrive than expected. So we'll move now over to how you actually get this effect and how we get to something that looks like a change to the arrival rate of the pulses that are getting to Earth as caused by gravitational waves. So my notes for this are already in the repository. But as yesterday, I'll go through things step by step so you see how it's done. If Zoom wants to connect to my app. Oh, thank you. Yeah, so it's actually showing up now, which is good. All right, so we start off with this very simple picture here of gravitational waves passing through the Earth pulsar system. So the distances here are between the pulsar and the Earth, we're talking about kiloparsecs, really. Thousands of light years. And with my limited artistic skills, I've tried to convey that by the time the gravitational wave gets to the Earth pulsar system, it's essentially a plane wave. Okay, so if we were actually closer to the source of gravitational waves, I'm not sure why that. If we were closer to the source of gravitational waves, then we'd have to take into account the kind of circular nature of the wavefront. But since our sources are hundreds of megaparsecs away, we can treat it like it's a plane wave by the time it gets to our galaxy. It's kind of ugly. So when it comes through. It wasn't this bad yesterday, was it? Well, maybe I had my iPad in low power mode, so maybe that's what's. Okay, we'll see if this works now. So we start off with our picture of what's called the space-time line element for a simple gravitational wave. The line element is kind of a generalization to different geometries of Pythagoras' theorem, except now we're working in four-dimensional space-time. And it's also another way of writing the space-time metric. So remember, before we had something that looked like G mu nu. Well, we can write this line element, which tells you infinitesimal distances between nearby points in four-dimensional spacetime. We can write this spacetime line element as this. And so when I write down the line element in this more verbose form, it allows me to also read off what the components are for the metric that I've got. So everything to do with the geometry of this spacetime is in here. And I hope you can see that to lead in order, this is just flat spacetime. This is Minkowski spacetime. But as we talked about yesterday, I've added my little perturbation on top of this flat spacetime. That is my gravitational wave solution. Okay, and for notation purposes, when I have I and j, it's going to be like x, y, z, or r theta phi. Those are spatial components. A and B are going to denote different pulsars. Okay. Well, I've given it away. I should have hidden this, but anybody that's taken a special relativity class or a GR class as well knows that the infinitesimal separation in spacetime for points that are joined by a photon path is 0. So for a photon path, ds squared, the spacetime line element, is equal to 0. That means when we set up this problem to look at the path of a photon that's propagating from the pulsar to the Earth, we can set ds squared is equal to 0. So let's do that here. I've got ds squared, which is now set to 0 for my photon path. And I just got this. And what I'm saying here is that I've got photon path being along the x-axis. So I've really got the photon propagated from some point on the x-axis to the origin, which is where Earth is going to be. And some other notation here, I've got HTT. That just means that we're keeping everything in that final coordinate choice we had yesterday, the transverse traceless gauge, which is the usual form that we're looking at gravitational waves. Okay, so I've got the metric perturbation H along the x-axis with this photon propagating through this slightly perturbed spacetime towards the origin. If there are any questions at all, let me know. In fact, there's already a mistake in here. That should be IJ. There we go. And this should really be XX, because it's the XX component of the gravitational wave tensor in the transverse traceless gauge. Okay, so I can rearrange this like here. I can just move the dt squared over to the other side of the equality, rearrange things, and then take the square root to get what dx is as a function of dt. So first of all, I start off with dx squared is equal to 1 plus h to the minus 1 dt squared. But we're dealing with very, very weak gravitational waves, very, very small perturbations to our background spacetime. And so I just Taylor expand this. So that 1 plus htt to the minus 1, if I take the square root of that, and then I Taylor expand, it gives me 1 minus a half. All right, so just a simple lead in order expansion. And whenever I take the square root of something, I can have a positive or negative solution. I'm choosing the negative solution here to correspond to this path going from a positive region on the x-axis, but going in the negative direction towards the origin. Any questions at all, just stop me. Same for people that are following along online. So we imagine now that we've got the pulsar at distance L away. So we can then take this infinitesimal form with dx's and dt's, and we just integrate. So we integrate with the bounds that we've got xp for the location of the pulsar, xe for the location of the Earth, and because of the direction I'm doing this integral in, that becomes minus L, the distance to the pulsar. And then I can do the integration over time between the time at which pulse was emitted and the time that it's received or observed. And notice here that I've got my expanded form, my approximate expanded form in here. So then it's not that difficult. You see, you're obviously going to get a term that is just T obs minus T emitted. And then you've got a little bit of an offset here, which is due to the influence of the photon propagating in perturbed spacetime of the gravitational wave. So just so everyone's still following along, L is the distance of the pulsar. This is the time at which the pulse is observed. This is the time at which the pulse is emitted. And then this is the relevant component of the gravitational wave metric perturbation. We're going to make another assumption again here that, as usual, and as we've used before, the metric perturbation is very, very small. So for most of our approximations, we can say that the observed time is equal to the emitted time plus L or C. Okay, I'm setting G equals C equals 1 here. So time equals distance. The observed time is just the emitted time plus the amount of time it takes a photon to propagate the distance L. And our photon, it's not being deflected. It's not being curved or anything like that. It's essentially traveling on a straight, unperturbed trajectory. And there'll only be very small modifications to when it actually arrives, caused by the gravitation. So this unperturbed trajectory is this x vector, and it's just along the position vector of the pulsar. So when I look from my location on Earth to the pulsar, that's the vector along which the photon is propagated. It's the line of sight. Now we can generalize all of this to an arbitrary direction to the pulsar. It doesn't have to be arranged so that we're looking just from the Earth to the pulsar along the x-axis. We can change it to the pulsar being in some arbitrary direction. It just requires a bit of a rotation. But when we go to an arbitrary pulsar direction in the sky, we're no longer just taking the XX component of our metric perturbation in the transverse traceless gauge. We've got the full gravitational wave metric perturbation, or at least the relevant part, that is the spatial components, ij. And then we just use the position vector of the pulsar, wherever it is on the sky, we just project the relevant components of the metric perturbation that we need. So that's what this is doing. Repeated I and J, repeated I and J, that implies a summation, or you can think about it like doing repeated dot products, where we're just projecting the relevant components we need of the metric perturbation onto the line of sight to the pulsar. So this is just a projection operation onto the actual position vector in the pulsar. Okay, so let's go back to the more to the form that we had for T obs and T emitted. So remember, we started off, we left things here. So let's rearrange this problem so that on the left-hand side of the equation, they'll have the observed time of the pulse, and on the right-hand side, it'll involve the emitted time of the pulse. That's what this is. This is the observed time of the pulse, is the emitted time, plus the usual light travel time between the pulsar and the Earth, and then a very small extra bit that's caused by the gravitational wave effect. So everything to do with gravitational waves is wrapped up in this incredibly small modification of this equation. If you had no gravitational waves, then your equation would be this. Okay? If h is 0, then this whole thing goes away. It's mostly the same as what we had above here. The only change that I've got is, instead of having hxx, I've replaced hxx by this projection to get an arbitrary gravitational wave direction, and that's introduced the general tensor, and then some projection operations involving p, the position vector of the pulse. So that gives us the observed time of pulse 1 in terms of the emitted time of pulse 1. But since we're looking at changes to the arrival rate of the pulses, we're going to look at another pulse, and that's going to be pulse number 2. Any questions before I go? Okay. So we're going to consider a second pulse that's emitted, obviously, one rotational period after the first one. So my second pulse is emitted at t primed, which is the original time that the first pulse is emitted at, plus p. So that's my rotational period of the pulsar. That means that the time between the observation of the second pulse here and the first pulse should just be the rotational period, but we're allowing there to be an extra little bit of something caused by the perturbation of gravitational waves. So again, without gravitational waves, our equation would be this. The time between the observation of the first and second pulse would just be the rotational period of the pulsars. But we've got a gravitational wave effect. So the good thing is we can reuse a lot of the work we had and just replace the emitted time of the pulse in our previous equation with emitted time plus 1 period. So we're going to reuse this equation and just replace some of the quantities. So I've got T emitted goes to T emitted plus 1 rotational period. And let's insert that into the equation we had above, the pulse number 1. So the observation time of the second pulse, which is T primed, becomes T emitted plus 1 period plus L. And then notice we've got some changes over here. So our integral goes from T emitted plus P. T emitted plus P is when the second pulse leaves the pulsar. T emitted plus P plus L is, roughly speaking, when that second pulse arrives at Earth. Remember, this is our approximation that when we do integrals like this, we can say that to lead in order, it takes T emitted plus P plus L. I've also got a change of the arguments that are given to my metric perturbation. Angel, did you have a question? Yeah. Yeah, it's a good question. Astrophysicists and physicists are lazy. So instead of writing G for Newton's constant and C for the speed of light, or even H bar for Planck's reduced Planck's constant, we said G equals C equals H bar. Okay. Yeah, it's so in the notes it's way up at the start for G equals C equals 1. When you actually have to calculate something, we take these forms where G equals C equals 1, and then we do dimensional analysis to put the G's and C's back in. Okay, so there's a little bit of work downstream to actually compute something physical, but it saves a lot of notation to just make things more compact like this. It's a good question. Any other questions while we're on this? Yes, we can. So the question was, for the interstellar medium and more terms added to the equation, you can consider everything to do with the usual timing behavior of the pulsar as wrapped up in this kind of thing. Okay, so yes, we're only assuming that the rotational period is the thing that affects the arrival time from the pulsar itself. So we're kind of assuming that it's a perfect rotator. But you could just modify this and say it's roughly some sort of function of all the timing parameters. So we can group everything that's deterministic and that affects the rotational period of the pulsar together, and it'll eventually just subtract away. All right, so in the first pulse, if I skip back up here, I had that Hij depended on time and it depended upon the direction that the pulse was propagating. And this is kind of taking the place of our distance. So if I multiply this by c, I'll get the distance. Here, I just need to modify this by the emitted time plus period plus L minus t prime. So it's really the same as up here. It's just I've added one rotational period. And to make this a little bit easier, I'm going to redefine variables to introduce something that's t double primed, which is t primed minus p. So I take this equation. This is exactly what I wrote in the previous page. So it's just repeating things. It's the observed time of the second pulse equals the emitted time of the second pulse plus the usual flat space time photon propagation, L, distance to the pulsar. And then I've got my gravitational wave effect, which is what I just wrote down. I redefine my variables a little bit to make things a bit more compact. So this is exactly what is written above, but just in my redefined t double prime variable. So I'm just replacing t primed minus p with t double primed, and that cleans this up a little bit. So notice that I've got t emitted plus p is now just t emitted in these double primed coordinates. This is where things get a little bit complicated, but we introduce an effect here by doing this integral that is related to the pulsar term. Some of you might have heard about the pulsar term. The first thing I'm going to do here is take this equation, which is just the observed time of the second pulse. I'm going to subtract the observed time of the first pulse, which I had way up here. So I've got T-obs up here. I'm going to take the observed time of the second pulse and subtract this whole equation from it. When I do this, I get observed time of second pulse minus the observed time of the first pulse. So leading order is just the rotational period of the pulsar. But then I've got my gravitational wave effect. So it's got two terms inside that integral. It's got the gravitational wave metric perturbation at this time and at this distance, and then subtracting the gravitational wave metric perturbation at this time and this distance. Okay, so there's a slight change here. We've got gravitational wave metric perturbation at some time plus the rotational period of the pulsar. And then we've got just gravitational wave metric perturbation at some time. So we need to look at how the gravitational wave metric perturbation might be changing over very small times, just the rotational period of the pulsar here. The rotational period of the pulsar is a millisecond. So P is roughly a millisecond. The period of the gravitational waves we're looking at is more like a billion seconds, 30 years. So 1 nanohertz is about 30 years when you look at it in terms of periods. So the periods are very, very different of the pulsars, which are part of our detector, and the gravitational waves, which is what we're trying to find. Big, big difference in scales here. That means that we can do an expansion of our gravitational wave metric perturbation and say that the metric perturbation at just one rotational period after is roughly the original metric perturbation plus a linear term. Okay, so this is just me doing Taylor expansion, where I do partial derivative of the metric perturbation evaluated at some time, multiplied by the delta t, the time offset that I'm evaluating. So metric perturbation at t prime plus p is roughly metric perturbation at t primed plus a linear correction. So it's a very, very small offset, just a linear correction. where the linear correction is proportional to the time offset p that I'm looking at. Does that make sense? Okay, so I'm allowed to do this because the gravitational wave itself is not changing that much over one rotational period, since the period of the gravitational wave is decades, period of the pulsar is milliseconds. Very, very different scales. So then I can take my delta p, which is really just the change in the apparent period of the pulsar, and divide that by the reference period of the pulsar. And that will leave me with just this linear correction term. So I'm allowed to cancel out everything else here because it will just subtract away. And I'm left with something that looks like the change in the period, or the apparent change in the period of the arrival rate of the pulses, divided by period of the pulses, is just given by this linear correction term here. Remember, these are projections to the unit vector of the pulsar. This is a partial derivative with respect to time. This is the gravitational wave metric perturbation in relevant spatial indices ij. So I still have an integral to do. I still have to do some integral over time of T emitted plus L. And to get that, I'm going to plug in some reasonable solution for what a gravitational wave could be. We saw yesterday that you can approximate a gravitational wave just like it's a plane wave in four-dimensional spacetime. So here I'm going to consider a monochromatic, that is a single frequency gravitational wave. And I can write this down just as a cosine. So this is going to be some amplitude tensor for my gravitational wave, which will depend on propagation direction of the gravitational wave. And then this is a wave that's propagating in direction omega, and it's propagated at the speed of light with some frequency, little omega gravitational wave. So taking this equation, plugging in this solution for what Hij is, I will get that the fractional change in the arrival rate of the pulses as a term that looks like this. I can just bring out this amplitude tensor with the other projection operations, which depend on the position of the pulsar. So I get a Pi, Pj, Aij. I've got repeated indices here for Ij, Ij, so that's taking care of all of the things that require a summation. Remember Einstein's summation convention, where anything that has repeated indices like this really implies sum over I with sum over j. Okay, that's taking care of my summations and my projections. And then when I do the derivatives, and then I do the integrals over time, I get something that looks like this, and this, which I can just write down simply like this. Okay, so it looks like I end up with some sort of geometry term that depends on the position of the pulsars. And then I end up with sort of the phase of the gravitational wave when it arrives at Earth. But then I also end up with another term that's subtracted off that looks like it's related to the gravitational wave when it's leaving or passing by the pulsar. Because this is offset by something related to the light travel time to the pulsar. So I've got two effects here. If I were only considering something like LIGO, I wouldn't get this second effect. It's because the gravitational wave effect on pulsar timing is an integrated effect over the entire path between the pulsar and the Earth. In LIGO, you're just looking at gravitational wave impinging on your detector, creating a strain signal, but we're not looking at strain signals, we're looking at timing effects. The timing effects are integrated over the strain signal. That integrated effect is what gives you 1, 2 terms. So if I rearrange things, the gravitational wave-induced redshift to the arrival rate of my radio pulses, which is just this, which you can also write as this, fractional change in the arrival rate of the pulses, has these two terms. And by taking my solution here, which was just for a monochromatic wave, and going back to a more general form, I get metric perturbation at the Earth, metric perturbation at the pulsar. This is what gives me these two effects, two important effects for pulsar timing array gravitational wave astronomy, called the Earth term and called the pulsar term. I can make this more compact by just writing this as a delta Hij, which you'll often see in papers or in review articles. And this thing here is important as well. If you take this kind of geometry bit and you put in something that has the polarization basis tensors for gravitational waves. So if I take, say, this, I'm going to call that geometry bit above here Dij. And then I take my polarization basis tensor for plus like this. So Dij operating on Eij plus, which is the polarization basis tensor for the plus polarization. I just get F plus. You'll have seen that in papers maybe as the antenna response function for a pulsar. LIGO has antenna response functions as well, which again are just a projection of something like this onto the polarization basis tensors of gravitational waves. When we do this, we get the polarization antenna response function for the plus mode in gravitational waves. So to be more explicit, F plus for omega for the A pulsar looks like this. I wasn't fast enough writing it. Okay, so that antenna response function that effectively controls the sensitivity of an Earth pulsar, a particular Earth pulsar system, to a gravitational wave coming from a particular direction, propagating in a particular direction, looks like this. And remember, this thing, Pi, is just the ith spatial component of the unit vector pointing to the pulsar. This omega hat is just propagation direction of the gravitational wave. The origin direction of the gravitational wave is just minus omega. And I've got a term here that you will only see in PTA gravitational wave astronomy. It's a denominator that goes as 1 plus omega dot p. If you look at the equivalent of the antenna response functions in LIGO, I think you just get something that looks like it's proportional to pi, pj. This is super important. This is a direct result of doing the integral over time, because the integral over time brings terms down into the denominator that involves 1 plus omega dot. Why is this so important? Well, I'll show you tomorrow, but this term here is the reason why the Hellings's and Downs curve, that correlation signature that we rely on for gravitational wave detection, looks asymmetric. It's a reason why it doesn't look entirely quadripolar. It comes down from a certain height at zero angular separation, goes negative, it's positive again, but it doesn't quite reach the same level as it did at small angular separations. It reaches a half level that it had. That's because this factor introduces some asymmetric response. What we're saying here is that we're more sensitive to gravitational waves coming from directions that are relatively close to the position of our pulsars than we are to gravitational waves that are coming from the antipodal direction, 180 degrees. So this asymmetric response gives rise to some of our correlation curves. Let me make this a bit more explicit, what the impact of the Earth and the pulsar term is. Okay, so here's a really nice picture that I think, I'm not 100% sure, I think it was originally made by Chiara to demonstrate what the pulsar term is doing. So I've got my binary over here that's really hundreds of megaparsecs away, emitting gravitational waves, and pretty much by the time it gets to us in our galaxy, we're dealing with plain gravitational waves. It might look like the gravitational wave hits the Earth first, and therefore, really the signature of the gravitational wave should be earlier at the Earth than it is at the pulsar. But really, remember, we're looking at an integrated effect over the propagation of photons to the Earth. It doesn't matter when the gravitational wave hits the Earth first, or even if it hits the pulsar first. It matters in the relative geometry of hitting the pulsars and then the photons leaving those pulsars and going towards the Earth. So really, the pulsar terms will always lag behind the Earth term. That means if we can pick up these pulsar terms, they'll give us an imprint of what this binary was doing, potentially thousands of years before the imprint of the Earth term. So we're only looking at snapshots of the behavior of these gravitational waves over something like decades, because that's how long we've been observing pulsars. But there is a kind of a secret imprint of what the gravitational wave was doing thousands of years ago. And it all combines together to give us these Earth and pulsar terms. The Earth terms will all be reporting the same phase of the binary dynamics. So no matter which pulsar we look at and look at the timing properties of those pulsars, they will all have the same phase of the Earth term. But the pulsar terms will depend on the location of the pulsar in the sky and how the gravitational wave passed by that pulsar. So we get different imprints depending on the relative geometry of the source and pulsar. The Earth terms are all the same phase, but if we have n pulsars, we'll get n separate chunks of pulsar terms that kind of give us little different bits of what the binary was doing, or the source was doing thousands of years ago. And if we can stitch all of those things together, we can effectively see what the binary was doing in evolutionary terms over thousands of years, even though we're only looking at a tiny snapshot of that history. The catch is that the pulsar term is really, really difficult to search for, and it's also very difficult to find. But since we're looking for probably monochromatic waves that are not really evolving much over the decades that we're looking at the waves, we rely on the pulsar term to give us some information about the evolution of the source. Because even though the gravitational wave signal will not be evolving much within a few decades, it will have evolved quite a bit over thousands of years. So the pulsar terms will have different frequencies, different phases than the Earth terms. If you want to see how that can happen, take a look at this. So this is the time of arrival induced delay along the y-axis here. This is modified Julian date, this is for a simple binary. I think it was for a billion solar mass binary in a particular pulsar. If I only had the Earth term for a particular frequency, for a particular source, then I'd get this dashed cyan curve. Essentially just a monochromatic wave. But when I include the pulsar term is much lower frequency, because when going from thousands of years in the past, remember gravitational waves cause the orbit to tighten, and so the orbital frequency increases. So the Earth term is a higher frequency than the pulsar term. So the reason why I've got this red kind of low frequency envelope surrounding the higher frequencies in this eccentricity equals 0 case, so this is a circular binary. The reason why I've got this apparent low frequency envelope is because that is the influence of the pulsar term. This lower frequency envelope is the low frequency of the pulsar term with the higher frequency information corresponding to the Earth term. So if we can capture both pieces of that, we can in principle disentangle the dynamics of the binary and see how much it's been evolving over thousands of years. And the things that affect the evolution of the binary are related to the mass of the binary. So we can use the combination of the Earth and the pulsar term to, in principle, figure out the total mass of the gravitational wave source. This is in a way similar to how LIGO does it as well. You look at how much a signal is chirping as it enters your detector and as it merges, and the frequency chirping of a LIGO signal gives you information about the chirp mass of the source. Things start to look a little bit more funky when you go to eccentric binaries, because if I only had the Earth term, this is the kind of behavior I might get for an eccentricity 0.5 system. What you're seeing here is the binary out here at apogee, so it's very, very far away from the other black hole. But then when it gets really high frequency here, this higher frequency area here, that's when it comes into perigee. So the black holes are close together. And then it's going back out again, gets low frequency, and then gets high frequency again. So these high frequency bursts are when the black holes are close together. Now, we also heard yesterday that gravitational waves cause orbits to circularize. So if something is eccentricity 0.5 at the Earth term, then what would its eccentricity be thousands of years before that? Well, it would be higher, and it could be something like 0.999, really, really high eccentricity. And so you get the combination of these high eccentricity pulsar terms, lower eccentricity Earth terms, giving you very weird, but still deterministic and still completely tractable waveforms that we can search for in our analysis. And this is a video. That's it. This is what we worked out before. This is the kind of redshift to the arrival rate of the pulses, or Doppler shift to the arrival rate of pulses. Don't think about this as like a cosmological redshift or any other type of redshift like that. This is just a shift or a fractional change to the rate at which radio pulses are arriving from these pulsars. So here I've got my geometric factors again, then I've got my change in my metric perturbation between the Earth and the pulsar, which I've written here. The lag time between the pulsar term and the Earth term depends on geometrical factors, projection factors, but roughly goes as L over C. And for pulsars that are kiloparsec distant, that could be thousands of years. If I plug in some representative numbers to figure out what the induced change to the arrival rate of the pulses might be, it roughly goes as the strain amplitude divided by the frequency of the gravitational wave. So if I'm looking at a 10 to the minus 15 metric perturbation, super, super tiny, a gravitational wave frequency of 1 nanohertz, which corresponds to a period of roughly 30 years, then I'll get a change in the arrival rate of the pulses of about 160 nanoseconds. And that's pretty huge. That's bigger than what we have actually measured from stochastic gravitational wave background. It's more like 100 nanoseconds or below. So we're dealing with smaller strains than what I've taken as representative numbers here. That's all I have for you. Happy to take any questions, but that is kind of the full derivation of how you go from here are pulses arriving from some regular clock out in space to here is how those paths of photons that we're using to time that clock are affected by the propagation of the gravitational wave. And it underpins everything that we use about antenna response sensitivity, these geometrical factors, and then the importance of the Earth and the pulsar term. So happy to take any questions. Thanks. Oh, okay. Let's see. Albert, I don't think we've had a question for you today yet.
So there's the difference of the binary.
Yep. Yeah, so the question was, there's a difference in frequency between the pulsar term and the Earth term. Is that due to the binary itself? Yes, it's the binary evolving as it emits those gravitational waves. Nikita.
Yesterday.
Yeah, so we'll have two different antenna response functions. So when we take those projection factors like PI, PJ divided by 1 plus omega dot P, and then we operate on the basis tensor of the gravitational wave. So the plus or the basis tensor for the cross, we get different antenna responses. So when we write down our waveform, and I'll get to that on Thursday, we have an F plus and we have an F plus. And we allow there to be different signals in those. So there's an S plus and an S cross. And also an important thing is that we have inclination dependence in these amplitudes as well. And depending on how a binary is inclined with respect to our line of sight, we'll get a little bit more plus or a little bit more cross. The optimal is to have the binary facing directly towards you like this. So your line of sight is this, you get equal amounts of the plus and the plus. It's like this, you only get plus, you don't get any plus. Seeker? Yeah. Yeah, so the question was, when doing the kind of linear expansion of the metric perturbation, why are we allowed to do that? It's because we're assuming that since the period of gravitational waves is years, decades, and the period of the pulsars themselves, or the rate at which the pulsars are arriving is milliseconds, the vast difference in scales there makes a linear expansion of the metric perturbation pretty appropriate. So it's a very good approximation that I can just say over 1 millisecond or a couple of milliseconds, the metric perturbation is just changing by a tiny amount related to the partial derivative of metric perturbation itself. Oh, Mercedes, you were trying to put your hand up. Who would answer that? Do you think you can wait until Thursday, though? Because we're going to, I know. Thursday is going to be a supermassive black hole binary bonanza. So we're just going to talk about the theory of binaries, and I'll introduce the theory of the gravitational waveform, and we'll also have Polina Petrov giving a tutorial on how we use our sort of de facto standard pipeline for searching for individual sources called QuickCW, because it's very quick compared to how we usually did it. It's very difficult. I'll say that because the pulsar distance is now a parameter that affects the frequency and phase of the pulsar term, then that means that we go from having to search over just like 7 or 8 parameters that would usually quantify the binary to now having those 7 or 8 parameters plus at least n pulsar other parameters, because each pulsar is at a different distance. So it expands the dimensionality, but we're already searching in hundreds of dimensions anyways. What's another 100 between friends? But we'll get to all of that on Thursday. Levi? That's a good question. So I've never done the calculation myself for introducing curvature to the waveform, but some people have written papers imagining what would happen if there were a gravitational wave source at the center of our galaxy. Like say there was a cosmic string at the center of our galaxy, and that way the source is then inside the network. Usually we're considering sources outside the network of pulsars. It does drastically change things though. Another thing that people have studied, I think Casey McGrath, who used to be a grad student at Milwaukee, has looked at being able to measure wavefront curvature effects and using that to help get better distances to the sources. And then using those sources almost like how LIGO uses standard sirens, where you might want to have the redshift of a source and the luminosity distance to a source. Once you've got redshift and distance, you can then calibrate the Hubble relationship and pull out things like the Hubble constant. So people have looked at being able to measure a few sources with wavefront curvature and trying to measure the Hubble constant PTAs. So if you're looking for a reference for the calculation, it would be McGrath. Put that in the slide. Okay. Not seeing any other questions in the room. Anything online? Okay, well, it looks like lunch has arrived. So in the room here, we're going to take lunch until 2 p.m. Central. Once we get back, we're going to talk about statistics, etc. Nima will give a talk on the theory of frequent distance Bayesian statistics. Kyle will give a demo on numerical implementation of those concepts, and that'll prepare us well for some more hands-on exercises tomorrow where we search for the gravitational wave background with our codes. All right, so for folks online, we'll see you in just about an hour and 45 minutes when we come back from lunch. Thanks. Ready. So welcome back from lunch. We've now got a lecture from Nina Law, who's talking about fellow here previously from States. We've been there, I'm sure. Nina eats statistics for breakfast. We're going to give you an introduction to everything you want to know about statistics. Probably a bunch of things you didn't even know you need to know about statistics. And if you're worried about statistics, scared of the concept of statistics, it's just the science of measuring stuff. So you do need to know about statistics, especially for women. So think of it.
Thank you, Steve. I just want to, before I begin, this is a physicist approach to statistics. I take a class from someone from the statistics department, they take it a lot more seriously. They talk about it in a formal sense. They have proofs for a lot of these things. Well, as physicists, we just want to use the minimal tools that we have a project, we care about the physics most of the time. The statistic is just a tool to get to the point that we want to get into. So it's a little bit here on an informal part. I'm not doing like heavy derivation or formal definition of these things because you see it once and you forget about it. I would like to talk about things that I actually do every day. So let's begin. Okay. Okay, it may sound a little bit silly that I want to talk about the need for statistics or probability. Well, it's kind of obvious, but I just want to give you a different perspective of why we need a statistic. By the way, this image was AI generated. I just typed in statistic and just came up. I had nothing to do with the statistic, but it just came up. So we all have gone through these introductory to physics courses, and there are these silly questions of the free fall. You have this object, you let it go, it falls down. Usually you're asked to determine what the velocity of the object is as it hits the ground. And there's a little disclaimer that comes up with these questions. It tells you if g equals 9.8, ignore friction, ignore this, ignore that. And sometimes if you go further in the graduate school or in undergraduate, they tell you don't ignore friction, model friction like this. Now imagine the same experiment, but you knew nothing about the experiment. You did not know the mass, did not know the friction, no one gave you the disclaimer, you didn't know what G was. It wasn't 9.8, you had no idea what it was. You had to measure all of that simultaneously. Imagine how hard that experiment would become all of a sudden. Just a simple free fall. You don't know anything about it. You want to measure everything simultaneously. It would become extremely difficult. Our job, for timing, is similar to that. I am interested in gravitational waves, but gravitational waves are not the only thing that is involved in this experiment. Other things are also involved. And we know absolutely nothing about it. Everything is interesting. We need to model everything simultaneously. And that makes it difficult. That's why we really need probabilities. Because we want to find a unique combination of these things that are all unknown that gives the highest probability that they can describe the data. I wish we lived in a universe where everything else, like the pulsars were completely known, the rotation period of pulsars, we knew everything about the universe except the gravitational waves. Then you would still need a statistic, but not to the degree that we need it right now. So I just wanted to talk about this to give you a perspective. This is a real application. It's usually you are not only looking for correlation signal or gravitational wave background, you're looking for everything else because everything matters. Now we'll switch on to talking about the principle behind it. This is just my opinion. These are all common sense. Again, maybe it's a physicist bias here. It's just common sense. There's nothing more to it. And this is like a simple example that usually people make. You have a coin toss experiment. You toss a coin 100 times, get 180 heads. Someone asked the question that is the coin fair? The coin that you use for this experiment, is it fair or not? And this is pretty common sense because you look at the data, it's 200 trials, 180 heads. You know, you have any common sense, you would say that the coin isn't fair. And the reason for it is right there. You know, the odds of observing 180 heads, or even more than that, in 200 trials using a paired coin is extremely low. You've always seen, you know how this experiment goes, you know this outcome is weird. So you make this conclusion that the coin is not fair. And that's frequentist. You just did a frequentist analysis on a simple data set. That's why I call it common sense. This principle, you already know all of this. And this whole idea, I know that this type of data is unlikely according to a hypothesis that I had last time. The last slide was the coin toss, the coin being fair. We just inherently did a frequentist analysis. That's what this frequentist approach is all about. So the philosophy of it, the way I see is that what we observe is a part of a larger set of outcomes. So this is a philosophy for this type of thing. We just observe random draws from many possible, perhaps infinitely possible outcomes. And the weird thing about this is that you assign probabilities to data. So you assume your models are fixed, but the data itself has probability associated. So the reason they call it frequentist is because data becomes frequency of occurrence of a certain outcome. So we can imagine there's somewhere in some extra dimension there's a box. All the outcomes of your experiment is inside that box. All you do when you make a measurement is you randomly draw some outcome from that imaginary box. That's the way that the frequentists look at a statistic. I hate to call it in comparison to frequentist. It's not a comparison. It's just a different approach. We have the Bayesian statistic, Bayesian approach to probabilities, and the philosophy is different. So what it is we just say data is what it is. You don't know if it's part of a larger thing. You have no right to assume it. Data is fixed. And we use data to update our prior information analysis. Again, data is fixed, not probabilistic, and assigning, in the Bayesian statistic, we assign probabilities to models instead of data. So these are two different approaches to probabilities and statistics. The frequentist, data is probabilistic. In the Bayesian sense, the data is fixed and it is what it is. And it often, when you have two different options, it's important to choose one for your specific case. And there's a lot of argument about some people in the field of astrophysics or even beyond that one is better than the other one. Usually people say that the Bayesian statistic is superior. I don't know about that. They all have their use cases. All that matters is that usually you need to use both. If you're working on anything, on a real data set, you don't even have a choice. Sometimes doing one is just not possible. So you're forced to take a frequentist approach or a Bayesian approach. It matters. You want to become a scientist, you're working on these things that you're familiar with both, and the data forces you to choose a side. So it's more of a discussion between the two different philosophies. When it comes to actual application, you already know what you need to do. Okay, that was a principle, and some introductory notes that you need to know about the basics of a statistic. I would like to talk about the process of now how you apply these philosophies, and I haven't really shown you any equations yet. So how would you take the data and look at it from the frequentist approach or from the Bayesian approach. So this is the most important sort of question that everyone has. So how do we get from data to infer parameters of models that aim to describe the data? We have data, we want to come up with a model, how to bridge this gap between inferring something from data about the model. So the first, I call it step 0, is think about the data, think about the model that tries to describe the data. And this model doesn't need to be something very complicated. Like the first step is to say data is uninteresting things plus interesting things. That's the beginning of everything in PTA data analysis. At least apart from just uninteresting plus interesting, which usually means you say data equals noise plus signal. That's simple. That's just a general form of the model. The more difficult part is to choose a likelihood function. This is the fundamental step in doing anything with probabilities about your data, is to choose a likelihood. And the likelihood function is always expressed in this conditional form. It's the probability of data given some model parameters. You can see the traces of frequentist approach in here. This is the fundamental quantity that the frequentists love to use, just a likelihood, because it's a probability of data given some. I will use E as a decoy for data and theta as a decoy for just a set of model parameters throughout this lecture. Then your job is to choose a frequentist or Bayesian approach. Again, you're forced into using one depending on the data. If you choose a frequentist approach, you need to explore the maximum likelihood conditions. In other words, you look at the likelihood, you find where the places that this likelihood is going to be maximum, and you find the optimal estimators. You will see an example of this in files sort of in maybe tomorrow, no more like tomorrow with frequentist optimal statistics stuff. So we'll see an example of this applied to the gravitational wave background searches. But the procedure is clear. You have the likelihood, you explore what happens if you explore the maximum likelihood conditions. If you take a Bayesian approach, then you've got a lot more work to do. So you have to follow what is called the Bayes theory, which is the expression of the philosophy of Bayesian approach in mathematics. So the thing that I just said about what the Bayesian approach is, this is just a mathematical approach. You have your updated information on the left-hand side. This is what you want to get. This is the sort of the goal of Bayesian statistics. Equals the product of likelihood multiplied by R, more on this later, divided by some minimization constant here, which is called evidence. That's the heart and the brain of Bayesian statistics, Bayes theory. You always write this equation down. I will talk about the prior a little bit, but just for now, the prior expresses how much I guess I rearrange this. The prior expresses how much information you have about the model before you look at the data. And this is the part that some people don't like about Bayesian statistics, because you've got to have some input into the probability before even looking at the data. Yeah, so it reflects how much you are willing to constrain the model parameters before looking at data. We're talking about Bayesian, sort of the prior probability. And it can be anything, really. It's absolutely your choice what prior you're going to use. Some priors are much easier to work with than the other ones. It's absolutely your choice. You need to know what prior to use. And that's the part that makes Bayesian statistics a little bit difficult. But anything can really serve as a prior. We have these uniform distributions. You just say, oh, all I know before I look at the data is that my model parameters are bounded between some minimum and some maximum. Or you can say, oh, the log of my model parameters are bounded between some minimum and maximum. Or you can say, well, my model parameters follow some type of normal distribution with a mean around some value and some covariance as well. But you have to express them mathematically before you can just take advantage of base theory. The cool thing about this is that just realizing that you're just expressing some template for a probability. You're not saying, well, the mean has to be this specific number, or the covariance has to be this specific number. This theta 1, for example, and theta 2, these are model parameters. You want to infer them. You're just telling the Bayes theorem that you expect the form of sort of the template for involvement of theta 1 and theta 2 is normal. And then the data is going to reshape. And then the fourth step is usually the one that involves a lot of computation, a lot of discussion, and years of work, is how well the inferred model describes the data. So you do model selection, you do hypothesis testing, you look at sort of the inferred model parameters, you think about them physically, whether they make sense or not. So this is the part that a lot of the work is focused on. Okay, 5 steps. Step 0 was about just looking, the thinking about the model, as simple as just sort of data plus interesting things plus uninteresting things. The next one was coming up with this likelihood function. Then you take a side, and then depending on the side that you take, you either go through the Bayes theorem or you explore the maximum. All right. Now let me give you an example. I don't really get into the specifics of things here in this lecture. The reason for it is because you will see the specific examples later. Gravitational wave background, you're going to see a lot of that. The continuous waves, and all of these are going to be explored. So you're going to see the specific cases. You're going to see the specific examples later. But I just want to give you an overview of how it would look like in an example of PTA. So this is the beginning of everything that we do with regards to pulsar timing and the statistics of the detection statistic. You write your part of the data set that you really care about, and you write it as contributions from timing model parameters, contributions from gravitational waves, and contributions from white noise. Now, this contribution from gravitational wave in reality is contribution from gravitational wave plus some other physics. But for the sake of simplicity, I only assume that our data is just affected by gravitational wave. So time model contribution, gravitational wave, white noise. In our field, people love Bayesian statistics, and they love to sort of follow the Bayesian statistic. But first, let's if you want to use Bayesian statistic, we need to find the likelihood in. So we write this sort of the first equation that I showed. We sort of rewrite it as noise equals residual minus timing model contribution minus gravitational wave contribution. It's just a re-expression of what I showed before. And we assume that the noise follows the mean 0 and covariance equal to some covariance matrix that is diagonal. We call it N. And then the likelihood of residual given the model factor this thing. Notice that in this equation, the only thing that's really unknown are these epsilon and A coefficients. Everything else is known. R is your data. M and F are basic matrices. I'm not going to talk about how they're constructed, but they're given to you usually, or you know easily how to make it. So the only thing that's really unknown is not A and the epsilons. The frequentist approach could be as simple as this. You say you want to take the derivative of this likelihood with respect to the coefficients B. I group the epsilon and A into 1, and I just call it B for the sake of simplicity here. You take the derivative of the frequency coefficient and find the maximum likelihood estimator equal to this very nice and simple thing. But this is like a frequency thing. The Bayesian approach is a little bit different. You need to introduce a prior. The prior that we usually like to introduce is something that looks like this. It's a normal distribution multiplied by another piece. I'm introducing another notation here. This capital B is a covariance matrix of these small letter b coefficients. And you just follow the Bayes theorem. You say, all multiplier for the coefficients and the covariance matrix is just a normal Gaussian probability multiplied by probability of B. I'm not specifying what that probability of B is just yet, but that's the choice that you're making, and following the Bayes theorem, you have the probability of your model parameters given data is this ugly thing. Some specific things that you can do, you can assume this covariance matrix B is sort of all of these elements is 0 except this the bottom right element, and this bottom right element has itself a prior that is log uniform. This is like a common choice that people make. And well, looks bad. What are you going to do with this? It's a lot of B's in here that we don't know. And the thing here is we don't know the coefficient. We don't know the covariance of the coefficients. In other words, we know nothing. So it would be much easier if we had the information about the covariance of the coefficients. But it looks like this. So what are we going to do with this? Well, let me tell you. What we're going to do is you're going to take advantage of the machinery of the Bayesian statistic. This is the part that really matters. This is the part where the sort of the magic happens. So machinery is called Monte Carlo simulation. Without it, it's clear that the Bayesian statistic is pretty much useless for most practical cases where your model parameters have huge dimensions. And we thought about it and how I would like to express Monte Carlo simulations. We get used to it when you use it for such a long time. You may have a hard time explaining like why does it even work. But the idea is like this. You have 1,000 monkeys here working on 1,000 typewriters. And somehow those 1,000 monkeys are assigned the task of turning that Bayes theorem into some numbers. And they will do it. You will see why. You're turning chaos into order. So the monkeys are your processing units. They're your computing processing units. Monkeys are given, in addition to typewriters, they're also given a dictionary. The dictionary in this case is Bayes theorem. It's Monte Carlo algorithms, which we're going to talk about, and the condition of detailed balance, another thing that the monkeys need to know. The words in the dictionary are just random numbers. And the Shakespeare that the monkeys are tasked with writing is a posterior probability, is what was on the left-hand side of that ugly thing in the base here. All right. I have to talk about this because this makes everything work. This is called the condition of detailed balance. It tells you that the net flux of probability is 0 out of every point in the parameter space. Formally, it's introduced with this. If you have a starting point x0 and x1, the condition of detailed balance is this equation. The reason that this must be true, the monkeys need to know this, is because this mathematically guarantees that the posterior probability is a well-defined function. It converges to the values. In other words, you can make sense of it as things that are tangible. There's another condition that also needs to be true if you want to reach convergence. You want to get to a well-defined probability, and that's called the thing all it means is that every point in the parameter space needs to be reachable. This, again, is something that physicists don't really think about. It's common sense. This is sort of someone very wise looked at the detailed balance equation and said that it must be true because anything else would violate the detailed balance. The problem is these transition probabilities that you go from a starting point to an end point, they're not known in most cases. You need to guess what they are. And these guesses are they're called proposal distributions. The problem you're solving is you know one point in your parameter space, you know one number that must be true about your model parameters, and you want to get another point. And for getting from the first point to the second point, you need a transition probability. You need something that tells you how to move. And this P is supposed to do that, but you don't know exactly what it is for your case. So you approximate it with Q, but this Q is multiplied by this sort of this mean of one. This alpha is called the Hastings ratio. The mean is in there to make sure that probability does not exceed 1. It also needs to be in there for detailed balance to be satisfied. This guy, alpha, that I call weight, called Hastings ratio, is there again to satisfy detailed balance. And if you don't believe me, this is the derivation for a very simple case here of why the shape of that weight needs to be the way it is for this detailed balance, that equation to go through. I'm going to talk about it. If you're interested, just follow along. The derivation is pretty simple. You know why that choice of Hastings ratio is made, why this is specific things in their place. Again, this alpha is very important. It's called Hastings ratio. There's a typo here. I meant proposed points, not pimps. Proposed points, which result in a Hastings ratio is smaller than the uniform random number that's between 0 and 1, are rejected. This is the only criteria to reject or accept a new point. You'll get to see it live with Kyle's Kyle's demo of Monte Carlo simulation. You will see how things will work out practically, but this is the idea. You want to always go uphill, so you want to favor points in the parameter space that give you higher probability, but you also want to go downhill sometimes. You want to explore the entire parameter space, and this criteria that this alpha has to be smaller than the random number between 0 and 1 is going to help you explore the entire parameter space. Some bit of terminology here. If Q is symmetric, which means the probability of going from point 1 to point 2 is the same as 1 to 2 for this Q, then the algorithm is called the Metropolis algorithm instead of Metropolis Hastings algorithm. The other cool thing about this is that the Bayesian evidence, that integral in the denominator, that's very hard to evaluate, is no longer needed because all that matters is Hastings ratio. As you can see, these probabilities, it's a ratio. So the constant of proportionality, which is what the Bayesian evidence is, was in the denominator of Bayes' theorem, just doesn't matter. I really love this. This is something that I've been working on, been using for 2 years at this point, is skip sampling. If you have the luxury of writing your model parameters conditioned on the rest of the model parameters and the data, you can use a specific case of deep sampling where the Hastings ratio is always equal to 1. There's a very nice derivation of this. I'm not showing it because it's just too many notations and you probably won't see the flow of the derivation by just looking at it. But this is a special case of the Hastings ratio always being equal to 1. If you are able to experience the first conditional probabilities of every single individual model parameters on the rest of the model parameters and data. This is very rare, by the way. You often cannot do this because such a thing just doesn't exist numerically or analytically. This is the last time I'm talking about monkeys. I just want to point these things out, that the smarter the monkeys, the faster and more accurate the results will be to Shakespeare. So your implementation of the Monte Carlo simulation matters. This is how you make monkeys smarter. You write a better code. Gibbs sampling is like giving monkeys an actual Shakespeare and just page numbers randomized. That's what it is. You help the monkeys a lot by applying Gibbs sampling. And the more monkeys you have, the better. Get there faster. So GPUs and CPUs with high core count these days are going to help you get there faster, even though your Monte Carlo algorithm is not as efficient as Gibbs sampling. You may even get there faster than Gibbs sampling because you just have a lot more monkeys. And sometimes this doesn't work. You put so much effort into it, and the monkeys give you something that doesn't make sense. This is the whole story of what I've been working on for the past 8 months. Just sometimes the thing that comes out of the Monte Carlo simulation is a stuck because the data is weird, your implementation is not good enough. So this is theoretically guaranteed to converge. Practically nothing is guaranteed. You've got to be careful. Okay. There are these two things that I'm not going to get into it. There's a nice GitHub page on different flavors of MCMC. It lists like around 100 different algorithms with some simple explanation of what each one is. And there's also a demo in the bottom. This is a fabulous demo that shows you live how Monte Carlo simulation work. If we had time, I think we will have time. I'll come back and actually, I think we'll have. I'm just going to show this. Let's see. Oh, the Zoom people can't see it. Let me share my screen. Where? So this is like a live demo of how Monte Carlo simulation works. Let's see. This is standard. Okay. So the thing that you're seeing on your screen, there are only 2 model parameters. The target distribution of the model parameter 1 is to the left. A little bit hard to see, the contrast isn't great here. The second model parameter of the distribution of the target. And this Monte Carlo simulation is randomly proposing points, randomly rejecting it or accepting it based on the Metropolis Hastings algorithms that we talked about. And as you can see, it is trying to approximate this theoretical target distribution. And if I speed this up, you can see that eventually it will reach convergence. It's just going to take a lot of time, depending on what algorithm you use. Let's change this from the Monte Carlo Hastings to maybe Gibbs sampling. Gibbs sampling will reach convergence faster because you do all the work prior. You organize all the conditional distributions. You analytically determine them. For example, you say, oh, model parameter 1 is conditional on model parameter 2, and the probability follows like a gamma distribution. Right? Probability follows something else. So that equation knows exactly what it does. So you reduce some of the randomness with Gibbs sampling. And so this is a cool demo. I can play around with it. It has other types of algorithms in here. You can see it has some multimodal as well. So this nice thing about Monte Carlo simulations is that if your algorithm is good enough, your proposal distributions, the Q distributions are good enough, you're able to explore the entire space. So it doesn't, you're most likely not are always going to look for something as simple as, okay, like a Gaussian distribution. Things that are interesting usually have a lot of different features. All right.
lecture. I guess I have time for so much of this. Oh. Website can be found. Working about an hour ago. Okay. Hopefully it will work for you. So this is a link to all different, about like 100 different flavors of Monte Carlo simulation, but there's a brief description of what each one is and what each one does. All right. So I would like to stop here. We're more than like 70% in the lecture. I just want to know if you have any questions, because the rest of this is really going to be a little bit different than what I talked about previously. So if you have any questions, even on Zoom, about what I just talked about, it's the best time to ask it now, before I move on. Yes. You can have infinitely many parameters. Which algorithm are we talking about? Gibbs sampling? Well, the Gibbs sampling is step by step. So there are different iterations. Within each iteration, there is a step-by-step thing. There's a step-by-step process. So let's say we are in iteration 1, and you have 10 model parameters. So in iteration 1, you have the probability of model parameter 1 conditioned on the rest of the 9 model parameters. So you draw a random sample from that distribution analytically. Now you're done. Then you go to the second one, which is probability of your second model parameter conditioned on the rest of the 9 model parameters. And you go this over and over again, and you repeat this over many iterations. And this is the beauty of Gibbs sampling. You reduce the randomness of all rejecting or accepting things because you already know the final distribution of conditional distribution of your model parameters. There's no restriction on the number of model parameters, theoretically. Practically, you get into a lot of problems depending on the size of things, how covariant the model parameters are with respect to each other. Gibbs sampling is notorious for getting you stuck at different places, even if you have only 2 model parameters. Because if the model parameters are strongly covariant, you need to come up with clever ways to sort of kick things around so that they don't get us stuck. All right, I will get on to, oh, there's something in the chat. Oh, so it's late. I hope my voice is clear now. I think it becomes unclear when I move. I will try not to. Okay, model selection and hypothesis testing. This is maybe a sad reality, but all that people care about is just a single number that summarizes your research project sometimes. It's very good if you want to get funding. So also these numbers matter a lot. And to summarize everything, summarize data, summarize your model, summarize your entire research, these model selection techniques will give you that single number to summarize it all. I would like to talk about this. The reality is our data sets, specifically I'm talking about the pulsar timing, situation is like this picture here. The sort of the situation, the dolphin that we have is the middle dolphin. And we would like to choose
which one actually is the right dolphin, which one is the right creature to use here. The data is never clear about this. You're missing the head of this dolphin. You've got to guess, or you've got to decide based on what you already know, which one is the actual, which one is a part of the data set that makes everything complete, which model is going to fit your data better. And this is just a reality of things. Your data is never informative. Tell you everything. You've got to decide. You've got to compare different and see where things go. Now, the frequentist use the p-value calculation very often to do hypothesis testing. So the idea behind p-value is what is the probability that you can obtain your data and more extreme versions of your data just by the randomness nature of the data itself. Remember, frequentist is all about data being random. So what the questions they ask also has this undertone of randomness of data itself. So you want to know how likely it is just by randomness that you can reproduce your data. You have a null hypothesis, and then the interesting one that we call it alternative hypothesis. And you are comparing these two. And in order to compare these two, you go on and choose a threshold to see, okay, if I'm comparing two things, what should the threshold be? Should it be smaller than like 5%, 10%, or 90% for me to make a decision on which hypothesis is sort of the I need to accept and which one I need to reject. Usually this threshold is called the significance level, and the 5% is very common choice between common choice for people that love frequent hypothesis testing. All right. So it's an example of this, might be a little bit unclear what the objective is for the p-value, but again, let's remind ourselves of this coin toss experiment. You have 200 trials, you have 180 heads and 20 tails, and the question that is being asked is, can this data be generated by a random chance while the coin is fair given significance level of 5%? So this is like a complete version of this question. Quantity is called the p-value is this quantity. So binomial distribution is in there because this is a binary data. So it's yes or no, head and tail. So you have to use a binary distribution here. The sum is over data and more extremes version of data. So that's what I mean by more extreme versions of data. So you can have 180 heads or 181 heads or 182 heads. So you sum all of those extreme possibilities of your data. And then this sum gives you a number. That number is called p-value. If it's just too small, you say, well, it's you reject this null hypothesis. Okay. The more important thing, in my opinion, the one that's more robust, is this odds ratio. And this is really the final boss of the PTA detection and statistic. This is the thing that takes a long time to calculate, but it's very important that we do calculate. So as already shown, I already showed this, Monte Carlo simulation does not care about the Bayesian evidence because all you need is Hastings ratio and a bunch of random numbers. But this Bayesian evidence, which was in the denominator of Bayes' theorem, has a very important property that it tells you, if you compare the Bayesian evidences between two models, it tells you which model is actually more preferable by data. So this quantity odds ratio is introduced here. It's simply ratio of those it's the ratio of Bayesian evidences. It's the ratio of those integrals in the denominator of Bayes' theorem. And that ratio is multiplied by another ratio, which is the ratio of the prior probabilities. This first part is called Bayes factor. The second part doesn't have a fancy name, it's just a prior ratio. So when you hear the term Bayes factor, and you will hear it, even if you read the nanograph papers, you will see that this is we focus on this number. The Bayes factor, just the ratio of the Bayesian evidences. So what it tells you is the odds of a particular model being better than another model and explaining the data. That's just, what else do you want? This is like it's an important question that you're asking. Data and the odds ratio tells you what that is. The part that is very hard is, what should this ratio be in order for you to say one model is better than the other? So if you find the odds ratio and the answer is 10, what does that mean? Is it better than 3? Is it better than 5? Like, what does it really mean? And unfortunately, I can't tell you that because there is no fixed threshold. There's no significance level that you can trust. It really matters that you understand your data set through simulations. So you calculate these odds ratio, under controlled circumstances. You simulate data sets, you know what is already in there. You calculate the odds ratio, for different cases, and you build this confidence to say, oh, the odds ratio of 10 really means that one of my models is 10 times more likely than the other. So the number is robust, it's odds ratio, it's Bayesian, it's bulletproof. The meaning of it really depends on your case. In pulsar timing, I can tell you about the gravitational wave background detection. Even odds ratios as large as 1,000 may not be enough for you to convince yourself that one model is definitely better than the other one. It's not enough to claim detection of a gravitational wave background, something like that. But that same threshold of 1,000 in medicine, for example, could be unquestioned. So it really depends on what you're doing, the context of your data set. The other important thing about the odds ratio is that the prior preference for a given model also affects it. You may not like this one, but I do. So if I go back, this prior ratio, if you have some wacky model for your data and it has a very low prior of being true, that affects the odds ratio. That's just part of the philosophy of this, that the prior informations also, affect everything in Bayesian statistics. There's this whole idea of this, the important part of how to estimate of, well, okay, it's good. It tells you, it's a deciding factor for choosing one model over another one. But how do we go about calculating it? Well, it's actually a nightmare to estimate for most cases. You have a small number of parameters, easy to do. Techniques called nested sampling are capable of doing this. Just what you are doing, you are evaluating that integral. So z sub m equals the integral of d theta m. You want the answer to that integral. And nested sampling gives you that answer for a few model parameters. I would say less than 10. Really depends, but less than 10 would work fine. But if for anything more than that, PTAs, for example, you need some fancy algorithms. Hyperspace sampling is what we use in pulsar timing for detection of gravitational wave background to decide between models. This is just some way of calculating the Bayesian, the base factor indirectly. The other one is thermodynamic integration. If you're interested in knowing what these techniques are, you can just simply Google it and see what they're all about, but they're just different ways of estimating the base factor and cheating their way out of evaluating that integral numerically. I'm done. I just want to give you this whole thing. I just talked to you about the statistic, was like an introduction. I didn't really get into much of the specifics of pulsar timing or gravitational wave background, but this is sort of most of the things that we do. We do single pulsar analyses, and these single pulsar analyses are fully Bayesian. We model our pulsars as some type of noise that we call it red noise. You can think of it as just a noise that's contributed from gravitational wave background, plus some uninteresting stuff that is white noise. This is full evasion. We do the single pulsar. Then we search for a common process. They search for a common correlated process. You will get to hear about all of that tomorrow. But, you know, they're all just they use the same principles that I talked to you about today. Bayes theorem is being used in all of these except simulation and generating simulations. Bayes theorem is involved in all of this. And frequentist techniques, Kyle is going to talk a lot about them, are also important for us, even though some of us don't like the idea of frequentist analysis, but they matter. They make us get to our correlations faster than anything else. Thank you so much for listening. That's all I've got. Yes. It's an interesting question. I think what you're saying is correct. You have to do it. P-value is all it enables you to do is just compare it to a null hypothesis. You can't have two alternative ones and compare it. So you have to calculate two p-values directly, look at them. I'm not a frequentist, I've never done it, so maybe there are better ways to do it. But I know for p-value, all you can do is compare an alternative one to a null hypothesis. That's all you can do. That's all this is good for. So you're asking about the matrix to evaluate a convergence? Yes. Okay. There's a funny story for PTAs. There's only one. I'll get to it after I answer this question. Where do I see the change? Yeah, so the question is about, I'm understanding it correctly, how to choose between different Monte Carlo algorithms. Which one should you use? And the answer to that is that you often don't even have a choice because only one sampler is going to work for your case. The thing about this is that these are all concepts that sound very simple on paper, but when you actually go ahead and code it, you're going to see that you have a lot of problems. Recently, in the past year, things have changed. But if we forget the past year and look at what happened before, only one sampler actually worked perfectly for us, and we've been using it. So we didn't really have this question of which one should be used. Only one thing actually worked. It worked because all people put their efforts on making that particular sampler better. In the past year, things have changed. People have spent time on other samplers. Now we know that there are better, more efficient samplers out there that we can use, but you don't really have that many choices, honestly. If you go on Google and type in Python Monte Carlo, simulate Monte Carlo algorithms, the packages that you see are usually not going to work for your specific case anyway. So you've got to, wouldn't say always, but you have to write your own sampler because you understand your data, so you understand the parts where things are going to get us stuck, and only you can write something that is applicable to your case. So hopefully that answers. Tyler on Zoom, the question.
I'm wondering if you could talk a little bit more about interpreting the odds ratio in practice. I know you said there's no, set criteria, but I don't know, maybe you can give a specific example of how you'd go about deciding whether or not you should choose one model over the other based on the odds ratio.
So I was part of the search. I was the lead for the search, nanograph search for alternative polarization of gravitational wave background. And what we had this problem, we had two competing models for gravitational wave background. One had this nice Hellings-Downs correlations that you would expect to see from GR. The other one was the correlations that you expect from some other theory of gravity, for example, a Brand-Sticky theory that gives you a scalar tensor theories. Correlations look very different. When you calculated the base factors and you compare them, we saw that actually the scalar transverse one, the non-GR one, had the odds ratio, comparing the non-GR one to the GR prediction, the odds ratio was, if I believe it was like 60. So we were kind of worried, like, what does this mean? Does this mean that our signal is more non-GR than GR? And we spent a year and a half trying to understand what that number really meant. What we did to understand it really was to make simulated data sets. We made simulated data set. We injected a GR signal, but we modeled it as non-GR. We injected a non-GR signal and we modeled it as GR. So we did it both ways. And we calculated these odds ratios for these simulated data sets. And the thing that we saw was that 10% of the time, if I remember this correctly, 10 or 11% of the times, you favor a non-GR over the GR case, even if the non-GR case does not exist in your data set. So the odds ratio can tell you a lie. The odds ratio of 60 wasn't high enough. It could happen out of randomness of data. You would get a high base factor as high as 60 for your cases. So this is like a specific case. That's why I was talking about this, that there's not a single threshold. You've got to make simulated data set. You've got to, the meaning of base factor of 100 may not be what you think it is. The context of this needs to be explored for specific cases separately. Yes. We don't have a direct method to reduce dimensionality, although we are working on trying to do things in the frequency domain exclusively. So, the time domain analysis of PTAs will blow up very quickly because of, it's a time series. We use 67 pulsars. We are going to include more pulsars as we go into the future. So we want to still be using the same techniques we use. Some of them are time domain based. It's just not going to work. But we don't have like a technique to reduce dimensionality. What we've been thinking about is just do things exclusively in the frequency domain using those A coefficients that I was showing you, because they don't depend on the number of TOAs, they depend on the number of frequencies. That's one way we get out of this problem of dimensionality. We don't have any other way. We make our algorithms more efficient. Recently, there's been a sort of an effort to make things run on GPU so that even though we have a lot of model parameters gets big, but we use better hardware to handle it. But we don't have a way to reduce dimension. We don't use it. It's not really applicable to our cases. All right.
Questions.
So let's take 15 minutes break, and then we can move into the more demo portion that
There we go. All right, everyone. Hi, I am Kyle Versbach. And in this particular section, we will be learning about implementing a lot of the things that Nemo was talking about in his lecture here. And so this notebook here, which is on the GitHub, so if you have that downloaded or you have it cloned, then you should have it in the week 2 section, or sorry, day 2 section in the tutorials folder. And it's called Numerical Freak Bayes. And it is a notebook that will cover, how you make an MCMC. So you'll make an MCMC for yourself. You'll do some sampling on a very simple model, discover some of the pitfalls of MCMC, and then maybe even do some bonus activities at the end. So in general, this notebook will introduce you to building a data set and how you actually construct a data set. You'll generate that data set. You'll create a model for said data set. You'll create a log likelihood function. You'll create a prior function, and then you'll use those to make your own MCMC. And then finally, we will switch over to a better MCMC sampler, something that's a little bit more developed than a 10-minute tutorial can really get you, which is PTA MCMC. It's the one that most of the Nanograph software uses. And we will reanalyze that data set and compare our results. And then if you get all those done, which is a lot, I'm not asking you to finish it all, but if you do get all those done, at the end, there are 2 more bonus goals, which are to learn to destroy your signals in a data set while keeping the statistics of the data set the same. And then also there will be a little bit about creating the null distribution for said model. So there's a lot here, do not worry. But for this particular notebook, so I'll briefly go over it. I'm not going to run any cells for you all. But I think what might be best is if you all group up into small or large groups, it doesn't really matter, whichever you prefer, and just work through it together. If you ever do get stuck, there is a solution to every problem that I put in the notebook if you scroll down a little bit. So what that means is don't cheat, but you can also cheat if you want, it doesn't matter. It's a learning process. But yeah, and for folks on the Zoom, I will put you guys in a breakout room so that you can work together. I recommend somebody will share screen and maybe go through it together. I think that's probably the best way to deal with it. So the beginning of this notebook, we'll talk about generating a data set and how the data set, if you learn anything from this notebook, I think this data equals signal plus noise is probably one of the most important things to learn, because it is so simple, but it is also ridiculously powerful. Once you have that, we will introduce what our signal is going to be for this notebook, and it's just a simple sinusoid. Once you've done that, you're going to create a model for your sinusoid. And then once you have a model for your sinusoid, you're going to make a likelihood function based on that model. There's a lot of text here, but really, you're just going to be implementing that last little equation, which is very, very simple compared to what everything else before it is. Everything else before it is just simplifying it for you. I do recommend reading it. I know it's a lot. Once you have that, you can then, there are also, I do include lots of plots and diagnostic plots. So if you get something that's a little bit funky, please call me over. I will be happy to help. And then once you have your likelihood function, you're going to create a prior function. This one, as Nima sort of pointed out, is we will be using, it's called an uninformed prior, a prior that makes no assumption about what its values are going to be. And that basically just means it's going to be a uniform prior over a space. And the space is just defined here. Once you have that, you're actually going to make an MCMC. And I know that might sound intimidating, but I can assure you it's fairly simple. And effectively, you're just going to be creating the Hastings ratio, as Nima pointed out earlier. And once you have a Hastings ratio, this is actually the pseudocode for an MCMC, in case you're wondering. It's really not good. Once you have that, you'll have a Hastings ratio, and you can put that Hastings ratio into an MCMC. This is literally the code. This is all of it. It's not a lot. And I do recommend reading through it, just making sure you understand what the heck is happening. Once you have that, you'll be able to analyze the MCMC, look at the trace plots in the histograms. And once you have those, you can also look at things like corner plots, look at covariance between different parameters. I will talk about, there's a little bit about the pitfalls of using MCMCs, or at least this particular type of MCMC, because I kind of had to cheat a little bit, but it'll make sense when you get there. And then we'll switch over to using PTA-MCMC, just so that you have experience using it, and then we will reuse that tomorrow. And then, of course, at the end, we have some bonus tasks. The bonus tasks are basically just trying to get a base factor. We'll find that that's actually kind of hard in this case. And so we'll have to instead go through the null hypothesis testing, which is very fun. And if you get there, please let me know, because there should be some interesting results. Cool. Okay. And that's generally it. Are there any questions before we start? Because if not, I think it's best to group up. I would probably recommend at least 3 people per group, if not more. And yeah, go for it. I will put the Zoom folks into a breakout room, and I will join that breakout room, but not through here, so that I can listen in on their conversations. And if they have questions, if you guys ever have questions, let me know. Raise your hand, and I will at some point look at the Zoom, and I will see that you have questions, and we'll answer it for you.
I started a breakout.
Cool. Okay. So Steve has started a breakout room. You guys should be able to join at any point now. Cool. Make sense? Let's do it.
Maybe later. Not very programming.